The following message is best viewed on an oscilloscope.
So good morning, everybody, or good afternoon, and welcome to the fourth session on the Astro-particle and cosmology at the ICHEP. This is our last session today, and we are going to have a few talks on cosmic rays at the highest energies, neutrinos in the last session, and some other talks from the AMS and from the space use mission. For the speakers, the talks are, the allocated time is 25 minutes, and this means 20 minutes plus 5 minutes questions. I would also like to remind you that we have the Mattermost chat if you'd like to ask questions within the talks, during the talks, and I will take a look all the time at this chat. Also, you can write in the Zoom chat, and please, at the end of the talk, if you'd like to ask some questions, just raise your hand in Zoom. Now, our first talk is by, I hope I'm going to pronounce properly the name, Dumrongsak, and he's going to speak about the simulation of the neutrons in cosmic rays in the atmosphere. So please, can you please start?
Yes.
Good morning, everyone. My name is Dumrongsak Rodphothong. I come from Lamkhamham University, Bangkok, Thailand. Today, I'm going to talk about Monte Carlo simulation on the effect of air mass above the Princess Sirindhorn Newton monitor to atmospheric neutrons from cosmic rays. I have divided my presentation into 4 parts. First, background knowledge. I will talk about the cosmic rays and the Newton monitor. Second, methodology. In this part, I will explain the atmospheric model for Fuga Monte Carlo simulation. Third, results and discussions. And finally, conclusion. What are cosmic rays? Cosmic rays are high-energy particles from outer space. The cosmic rays are produced by the Sun and also produced from outer solar system by supernova explosion. About 90% of galactic cosmic rays are protons. You can see in this picture. When primary cosmic rays strike the Earth's atmosphere, then produce a cascade of secondary particles such as neutron, proton, muon, and gamma ray. Vertical geomagnetic cutoff rigidity. The primary cosmic ray move along the Earth's magnetic field to enter Earth's atmosphere. The Earth's magnetic field is protect us from cosmic rays. If we focus on Thailand, Thailand has the maximum magnetic cutoff rigidity in the world. The vertical cutoff rigidity is 16.8 gigavolt. That's the lower limit in rigidity for cosmic ray to pass through the magnetic field to the Earth. The Princess Sirindhorn Newton monitor, or PSNM, the first Newton monitor station in Thailand. It was set up at Doi Inchanon Mountain, the highest point of Thailand, in order to measure the count of secondary Newton, which is related to the flux of cosmic ray in space. To understand the ground-based Newton monitors as a primary particle detector, a relationship between the count and primary flux must be established. This is some information from Newton monitor that measure number of secondary Newton from the collisions of primary cosmic ray ions into the Earth's atmosphere. The main window of the Visual Basic program that records the Newton monitor data you can see in red circle. For the part of the simulation, we use the Monte Carlo simulation based on Flux. I think Flux is well-known software package to simulate particle transport and interactions with the matter. In this work, the data from the Flux input are including particle source, definition of geometry, materials detector, and a random number sequence to start the simulation. And for the Flux output are including the type of secondary particle, energy, and type of interaction that let us know what happened during and after the simulated interaction of the request particles. The first step of the Flux simulation, we put the specific data consists of atmospheric structure 100 layers with 300 primary protons of 1, 10, 17, 20, and 30 giga electron volt for this model. We start at the top of the atmosphere, about 51 kilometers above sea level. After the Flux simulation, we got the output. The output are the particle type, kinetic energy, direction, and position of each particle in each layer. This is a final atmospheric model for Flux of this work. We divided the atmosphere into 100 layers within a rectangular box shown in this figure. We set 20 kilometers of horizontal length for each side and calculated the atomic composition by using the molecular weights for each layer. Moreover, we created the ground region at 2.5 kilometers of altitude with granite. Most of the rock at the Inchanon Mountains to model the particle propagation through and interactions in this region. For the result, the first simulation show the atmospheric cascade in standard dry air from five monoenergetic 1 giga electron volt primary protons. You can see the x-axis show horizontal of total length 20 kilometers and y-axis show the altitude of maximum 51 kilometers. For the big blue point on the top center of the simulation box is primary protons. For the PSNM station level at 2.5 kilometers represented by the blue solid line. In this case, we are considered in standard dry air. For this simulation, we select only 5 models of secondary particles. The result represents some of the secondary particles were absorbed before approaching the PSMN stations as indicated by a solid line. The different colors show the type of secondary particles such as blue point represent proton, green point represent neutron, and black point are gamma rays. For the next simulation, considers atmospheric cascades in standard dry air from 5 primary protons with energy 10 giga electron volt. We do the same way as select the 5 models. You can see in the that the blue solid line as the PSMN station level. Only the last model have a few secondary particles reach the station such as gamma rays, muons, and neutrons. For higher primary incident particle of 17, 20, and 30 giga electron volt in the standard dry air can produce more secondary particles and lead to the station, especially the cascade from 30 giga electron volt clearly represent the number of secondary neutrons and gamma rays are lead to the station. On the other hand, we try to simulate a more realistic simulation, take the effect of rocks, mainly granite, into account, because the granite rocks is the primary geological setting of the Neutrinos mountains. The red solid line are the granite rocks. For all energy of 17, 20, and 30 giga electron volt could not penetrate the rocks, but there are some secondary particle reflect. For my discussion, we have to take action on the relationship between neutron energy and neutron flux of standard dry air and effects of granite rock to secondary neutron. You can see that both simulations of standard dry air and rocks are represented by the Flux simulation. We calculated only the secondary neutron flux from 17 giga electron volts of primary proton at PSNM station that located on the Neutrinos mountains. altitude of 2.5 kilometers above sea levels. The results show low energy neutron flux of standard dia shown in figure A is lower than neutron flux of logs that shown in figure B. Because some neutrons undergo spiration or reflect and lose their energy at the logs, then spreading upwards to form a cloud of lower energy neutrons, which can thermalize and diffuse downwards again with lower energies. In the same way of the relationship between the neutron energy and the neutron flux, we will consider the neutron flux of affecting Ganit logs with compared to the previous works of John Clem from the University of Delaware. He worked on the same study area at the Internal Mountains. You can see that both results show consistent neutron spectrum at PSNM station for all energy considered, including a main peak at 100 mega electron volt and a tail of low energy neutrons at about 1 mega electron volt. Moreover, the results showing the sub-giga electron volt neutrons can easily penetrate the station and thus result in most of our PSNM coverage. In conclusion, this work we have performed a nucleonic cascade simulation by using Fuga program. We developed the input files for Fuga and simulated the effects of the secondary neutrons on air molecules by taking the effect of log into account. The results show the expected neutron energy spectrum at the internal mountains, that is the neutron produced by atmospheric cascades and could be detected by neutron monitor. This work will give us data for further analysis and better understanding of effects of the atmospheric structure on neutron monitor counts. We will also obtain information that can be applied to improve space physics and astrophysics knowledge. Thank you for your attention.
Thank you very much for also for keeping in time. We do have some time for a few questions. Let me see if I see any hands raised or in Mattermost. So it seems that from the public there are no questions, but I do have a question. So are you also planning to simulate different atmospheres? I don't know how strong is influenced the neutron flux that you are going to expect on summer, winter atmosphere, and how much the density of the atmosphere is influencing your results.
เขาอยากรู้ว่าตอนที่ simulation นะคะที่ว่าอากาศกับนิวตรอนมันเกี่ยวกันยังไง
When primary cosmic ray interact with atmosphere, there are reaction that reduce the energy of primary cosmic ray, and then it's produce many secondary cascades in the air. But in sea level, there are a little particle to the Earth at sea level.
Okay, thank you. So any other questions? It seems that no. So thank you very much, and thanks for giving this clear presentation. And we are going to switch now to two of the talks from the Pierre Auger Observatory, and the first one is David Schmidt. And he's going to speak about how you test hadronic interaction models in Auger. David, please.
Okay, does that look all right?
It's perfect. Thank you.
Great. Good morning then, afternoon, whatever the case may be. So as introduced, today I'll be talking about the tests that we can do of hadronic interactions with measurements of the hybrid detector of the Pierre Auger Observatory. So just first things first, to discuss the beam that we have to test these interactions, we can take a look at the cosmic ray energy spectrum. And so what we see here in this plot is the flux of cosmic rays scaled by some energy factor as a function of the energy of these primaries. And you can see that for the Pierre Auger Observatory, these measurements extend in the lab frame all the way up to 10 to the 20 eV, which is a massive energy. Should you calculate it in the proton-proton center of mass, it would be well over 100 TeV. Of course, at these energies, we have an incredibly low flux as well, where you would expect maybe 1 particle per square kilometer per 100 years. But as you move to slightly lower energies, because of the steeply falling flux, which falls at around something like the factor of proportional to e to the -3, you get a massive increase in the statistics fairly quickly. So this is the beam that we're talking about. There's some further complications in this beam, of course, and I'll get to those in just a few slides. But this is what we're working with. Now, these cosmic rays being so rare, of course, we can't detect them directly, nor is that necessarily what interests us in this case. And so our target is the air. And when a cosmic ray enters the atmosphere, it will first hadronically interact with either a nitrogen or an oxygen molecule in the atmosphere. And this first interaction initiates what's known as the hadronic cascade. So first we have this ridiculously high energy hadronic interaction, and we have a cascade which is largely made up of pions. Neutral pions are produced in this cascade and fairly quickly decay into 2 photons, which then fuel a electromagnetic shower through iterative Bremsstrahlung and pair production processes, which you can see here on the left of the schematic. And then we also have charged pions that are produced in this hadronic cascade, and these either go on to interact again, unless they fall below some critical energy, at which point they can decay, and they can decay into muons, which are represented by the green portion of the schematic here. And typically then we talk about, in a very basic sense, 2 components of these air showers, the electromagnetic and the muonic. However, the real picture is of course significantly more complicated, meaning the electromagnetic cascade can even go back and produce muons again through photoproduction processes. And you can also get decays of muons that again give you electrons, and as well as you can have low energy pions that are more tracing the hadronic cascade that can also produce electromagnetic particles that would more trend with the hadronic component as opposed to this pure electromagnetic component. So the real picture is of course much more complex, but in a basic sense, to a first order model, we can divide this up into 2 shower components, muonic and electromagnetic. Of course, what complicates this whole study is composition as well. And what's meant by that is that a given energy in the spectrum, we don't necessarily have a pure beam of particles of the same mass. And in fact, as we change the energy that we're examining, we might have different contributions from different mass groups in our beam. where the higher mass primaries, where you have more nucleons, will induce showers that have a larger hadronic component. Whereas if you had a primary that had fewer nucleons but the same energy, you would have a smaller hadronic component. Whereas the energy that's fed into the electromagnetic component remains more or less the same in both cases. And so when we want to study hadronic interactions using an experiment that measures ultra-high energy cosmic rays, we want to have a feeling for what the mass composition is. However, to know what the mass composition is, we need to have models that well describe the hadronic interactions in the shower such that we can interpret our data. But to do this, we need to know the mass composition. So we have, of course, the cyclical dependency when studying both of these, where one depends on the other. So it's a bit of a complex situation. So the instrument that I'm talking about, or on behalf of today, is the Pierre Auger Observatory, which measures these air showers. It's located in Malargüe in Mendoza province in Argentina. And it's a hybrid detector that consists of a fluorescence detector where you have 4 sites. And these telescopes of the fluorescence detector overlook a 3,000 kilometer squared array, which is made up of these surface detector stations, where each dot in this map represents one such station, that are spaced at 1.5 kilometers from one another. These showers come incident on the array, and the longitudinal profile, so the development of these showers in the atmosphere, is measured by the telescopes, and then the particles that reach ground are sampled by these surface detectors. The energy threshold for our measurements goes down to around 10 to the 17.5 eV, largely due to a small region of the array where we have a more densely spaced water Cherenkov detectors, which allow us to go down to these energies. The higher limit of energies being closer to the end of the spectrum, this 10 to the 20, or a little bit higher, as discussed before. So just to go into a little bit more detail on the detection principles, we have, again, a cosmic ray that comes in into the atmosphere, interacts with this oxygen or this nitrogen molecule, and initiates a cascade from which develops this electromagnetic cascade. The profile of this electromagnetic cascade is something we can measure with the fluorescence detectors, because as these charged particles pass through the atmosphere, they excite nitrogen molecules, and then the decay of this excited state releases photons, which we can then measure. So we measure this profile with the fluorescence telescopes, and when we integrate this profile, we get a calorimetric measurement of the energy of the cosmic ray primary. Now, when these showers reach the ground, they also have many, many particles that reach the ground depending on energy. It can be a footprint of tens of kilometers squared even, energy in zenith angle. And we sample these particles that reach ground with the water Cherenkov detectors. So these particles enter the detectors and deposit energy. We measure some signal that's proportional to this energy as a function of the arrival times of these particles in the stations. And we do this at different distances from the shower axis, depending on where the shower core landed and where these stations are positioned relative to the shower axis. And so what we can do is reconstruct something called the lateral distribution of these showers, and using the predicted signal at a given distance when fitting this distribution, we get a quantity that we can calibrate with the calorimetric energy from the fluorescence detector in the circumstances where we had measured with both detectors the same showers. And once we have this calibration for events that are just measured by the surface detector, we can go back and, using this calibration, get an energy estimate from each measurement. So this is the basic measurement principle and the quantities that we have available to us with the Auger Observatory. Just to talk a little bit more about the electromagnetic profile. So this is the electromagnetic measurement that we have of these cascades. We use a Geiser-Hillis function to fit the shape of this longitudinal profile, and it's something that fits rather well, at least within our measurement uncertainties. It's also important to note that it's universal for primaries of different mass. That is to say that the shape of this profile is the same, for instance, between proton and iron primaries. Here you can see the energy deposit as a function of depth, where the iron and proton profiles have been laid on top of one another, so that you can see the similarity or the nearly identical shapes that they have. This is something that we can make use of, this universal profiles, because although the profiles may have the same shape, they do not develop necessarily at the same point in the atmosphere, which brings me to the measurement of the depth of the shower maximum. So when you have a very heavy primary, where you have many nucleons, the first interaction may happen higher in the atmosphere, and the showers develop higher in the atmosphere. And so you reach the depth of shower maximum, so where you deposit the most energy, higher in the atmosphere. Whereas for lighter primaries where you have fewer nucleons, they can penetrate much deeper into the atmosphere, and they give you a deeper depth of shower maximum. What you can see with the measurements of Auger, looking at the plot here in the top right, for instance, is you can see the average depth of the shower maximum, where we have model predictions for the heaviest primaries that we might expect, being iron, and the same predictions for proton. And you can see that you have a difference of around 100 grams per square centimeter in this average depth of shower maximum. You can also note that up until a little bit above 10 to the 18 EV, the spectrum or the composition of our flux seems to be getting lighter. And then over this energy, you can see a steady increase to heavier masses in our flux. Of course, the average depth of shower maximum isn't the only measurement available to us using the depth of shower maximum. We can also look at the fluctuations, where lighter masses that penetrate deeper also have larger fluctuations shower to shower and where this depth of shower maximum is. And if you plot analogously the fluctuations in the maximum of the shower, you can see that the same picture, we have a very light flux up until a bit over 10 to the 18 EV. And above that point, we have a steady increase to heavier primaries in our beam, in our flux. So one thing that we can make use of, considering the energies where we still have a very light flux that is largely protonic, is we can take a look at the distributions of this depth of shower maximum. And we can know that the deepest penetrating showers in this distribution, we already expect most of it to be made of proton primaries, but the, say, 20% most deeply penetrating showers are almost sure to be proton. And the exponential fall off of this distribution is intimately related to the cross section that these protons would have in these primaries in their first interaction in the atmosphere. So what we can do is we can fit the tail of this exponential, we can get this slope, and we can directly relate it using hadronic interaction models in a way that is actually independent of the hadronic interaction models, because they give the same relationship between the cross section and the slope of this falling edge of the X-max distribution to reconstruct a cross section in a way that is relatively independent of the hadronic interaction model used. And this is exactly what we do in Auger for, at this point, up to 2 energy bins, which you can see the center of mass energy for a proton-proton collision shown here on this slide. Once we have that proton-air cross-section, we can also, using Glauber theory, convert it to the inelastic proton-proton cross-section. And the largest source of systematic uncertainties that we have in this whole procedure is just the chance that we did have a few helium primaries that got in the mix of the sample that we were using to derive these cross-sections. And this amounts to something like a 6% bias if your helium fraction stayed below 25%. So that's something we can do with the pure electromagnetic measurement that we have in Auger. Something else that we can do with these pure electromagnetic shower profile that we're measuring with the fluorescence detectors is take a look at a set of very high quality profiles at, say, an energy for this study between 10 to the 18.8 and 10 to the 19.2 EV. And here we have a zenith range where we look from 0 to 60 degrees. And we can look at these high quality measured profiles, and we can take simulated profiles that match for different primaries that represent, or that well reproduce the shower maximum and the shape of these profiles. And if we have the measured profile and we have the simulated matching profiles, we can also look at the particles from these simulated matching profiles that would have reached ground. So for the same showers, what does the particle footprint look like? And then we can go ahead and simulate that particle footprint, and we can compare it to what was actually measured when these showers reached ground in our real measurements with the detector. And what we can do then is we can look at the difference in between what was predicted and what was measured, and we can define a rescaling factor for these signals, which is rescaled in terms of 2 rescaling parameters, one related to the total energy, which would affect both the electromagnetic signal and the hadronic signal, or the signals coming from particles from these 2 components, as well as a parameter that would just scale the hadronic portion of the shower. And when we define this rescaling parameter and we use our full data set and we perform the fit, we can get these rescaling factors, which are then shown on this slide here. And we can see that in all cases, with the different assumptions that we've tested, we see no need to rescale the total energy. However, we do see an incompatibility of the hadronic component, so, these signals, such that they would need to be rescaled by a factor of between 1.3 and 1.6, where The least significant case would be using the EPOS LHC hadronic interaction model, where the composition assumed from our depth of shower maximum measurements, as mentioned before, this composition is assumed in assembling these profiles in order to do this study. And here we have a significance of this discrepancy in the most pessimistic case of 1.9 sigma. So this is one result that uses both the electromagnetic shower measurements that we have, as well as using the surface detector measurements, which measure both particles from both components at ground. Something else we can do with our surface detector is using very inclined showers, where these very inclined showers that have zenith angles beyond, say, 62 degrees, where we use different methods, are very, very attenuated, meaning there's very little electromagnetic component left, and it's mostly muons that arrive at ground. What we can do is we can construct muon maps from simulations. So what we expect the lateral distribution of these muons to look like at ground. And then for real showers, we can fit to these distributions, and we can have a scaling parameter that tells us what is the magnitude of the shower, how does it differ from these templates that we have, and we call this parameter N19. And then through this ratio, we get our mu, which is a parameter sensitive to the muon content of every given shower in our measurements. What we can do then is we can calibrate our mu that we get for each shower in terms of energy, such that we get an energy calibration. So for any given R mu, we can reconstruct the energy of the shower by calibrating with measurements of the fluorescence detector once more, this calorimetric energy estimate, similar to what was described for the standard ST methods a few slides before. With this in hand then, what we can do is we can plot the R mu as a function of energy, and we can observe not only the absolute scaling of this R mu relative to predictions from different hadronic interaction models for different masses, but we can also see how this evolves in energy. And what we see is that indeed we have a prediction that well exceeds even iron, which is in conflict with the predictions for mass that we had using the depth of shower maximum, which again was an electromagnetic estimate of composition. Just to look quickly at these results and to summarize this statement in a plot, here you can see this natural log of R mu. Here you can see average X max. So here I have an electromagnetic estimate of composition. Here we have a muonic one. And here we have the Auger data. And you can see that it's not compatible. So we can't get a comprehensive description of the observables that we have in Auger with the hadronic interaction models in their present state. And if we lend confidence to the electromagnetic measurement, then it would imply that we have a deficit in the simulations in the number of muons that are predicted using these hadronic interaction models. So here on the right, we can see just this average natural logarithm of the R mu parameter. And you can see that, again, it's compatible essentially at best with iron, but it mostly exceeds this. And we can also look at the rate that this R mu estimate changes with energy, and we can compare that rate to what we had before. This is what we call the elongation rate. And you can see that we have an incompatibility in this as well. So something fishy is going on here. There's a discrepancy. Something else we can do with the detectors that we have in Auger is we also have a set of buried scintillator counters, which are 30 meter squared scintillators buried at 2.3 meters below the surface at 7 water Cherenkov detector locations at present. We can do a very similar analysis to what I described before, in that we perform some energy calibration, and then we look at how the density of muons measured with these detectors changes as a function of energy. And we see, again, this difference in the absolute scaling. We see a prediction much heavier when interpreting with the current hadronic interaction models or simulations performed with these models than what we got with the electromagnetic estimate. So a much heavier composition, again, implying that we're measuring more muons than what's predicted if you lend confidence to the electromagnetic measurement that we have. Just putting these together for an interesting view side by side. This measurement with just these few muon counters, of course, it's a much smaller area of the array. We can only measure at lower energies where we have a larger flux. Here we have this R mu estimate from before. Here we have at the higher energies with these inclined showers. And you can see here this break in the evolution of this R mu parameter in energy. It's actually just interesting to note that this is also this inflection point where the composition is estimated by the electromagnetic component changed, which is in this gap where we don't have measurements with these two muonic estimates. Just an interesting point. Something else David, we can do?
You have 5 more minutes.
Okay, thank you. So just one more measurement that we can do is of the muon production depth. And this is where we can look if you can get an estimate of individual muons and their arrival times in water Cherenkov detector stations, which you can often do at larger distances from the shower axis where you can really see these individual muons. And you make the assumptions that they have straight rectilinear trajectories and are produced along the shower axis. If you have the geometry of the shower, then what you can do is just from this timing is you can get an estimate of where this muon would have been produced on the shower axis. And then you can look at the distribution of where these muons were produced and you can find where the maximum production depth of these muons was. This is analysis we can do and we have done. And here you can see the results just looking at the average depth of shower maximum as a function of energy, as well as the fluctuations therein. And it paints a similar picture to the other estimates of composition that we had with other muonic measurements. This, of course, by nature being a bit different, but you can again see that our predictions well exceed iron for the EPOS interpretation, as well as are more or less compatible with iron for QGS-CHEP, which is again at variance with the pure electromagnetic measurement of composition that we see here. One other thing we can do is we can look at rise times. So in the surface detectors, we measure particles coming from both components, the muonic component of showers, as well as the electromagnetic. And we know that muons arrive earlier on average than the electromagnetic particles due to their rectilinear trajectories and high energies and non-diffusive movement through the atmosphere. And if we integrate the signal and we look at the time it takes to reach from a 10% integrated signal to a 50% integrated signal, this is something that would be sensitive to how much of each of these components that you have, or how many muons you have arriving at the station versus electromagnetic particles. We can take a look at this rise time, and then using a benchmark, we can combine the rise times measured for different stations in the event, and we can again get an estimate of a quantity that should be sensitive to the mass of these particles, or the muon content in showers, which would be sensitive to the hadronic component of these showers. And here you can see these results, and we see that while over predicting the composition, or predicting a heavier composition than what we would from a pure electromagnetic estimate, it isn't as excessive, so it doesn't predict as heavy of a measurement as some of the other purely muonic based estimates of composition. So this is a measurement that's sensitive to both components, and accordingly it predicts something that isn't quite as heavy as the pure muonic estimates, which again is in line with the conclusion that we have a deficit in the number of muons in simulations that we have. So just to quickly summarize then, the hybrid design of Auger and the different detectors that we have, surface detector, fluorescence detector, and even buried muon counters, allows us to get estimates of the electromagnetic component of showers, and then through muons, an estimate of the hadronic component of the shower, so the magnitude of these components. But this measurements are heavily complicated by composition. Through looking at the fact that we can't comprehensively describe our composition or interpret our composition with the models that we have, we get a different result when using electromagnetically based interpretation or a muonic based interpretation. We conclude that we have a muon deficit observed in the simulations. And here below, I just have a quick summary of which analyses I covered in this presentation and which detectors they used. So not quite to the end yet, just one more minute. And that is that in the future, we plan to enhance our ability to decouple this interpretation of hadronic interaction models with composition by adding a scintillator detector on top of each water Cherenkov detector. Now, why would we do this? We would do this as particles of the electromagnetic component of showers have a different response in the scintillator than they do in the water Cherenkov detector. Take, for example, an electron and a muon would deposit about the same energy in the scintillator, but a muon, which would pass through the full depth of the water Cherenkov detector, most likely, would deposit a much larger signal in the water Cherenkov detector. So these two detectors have differing responses and may allow us to detangle the muonic and electromagnetic component of showers, which again would allow us to get an estimate of the mass composition, which would allow us then to perhaps select a more pure beam, or to account for the fact that we have a non-pure beam in our analysis and better study hadronic interactions. This isn't the only component of the upgrade that Auger is going through, but of course there was a talk already on Tuesday that gave much more detail on the different components of this upgrade, which you can refer to. And in considering time, I will go ahead and leave it there and ask for any questions.
Thank you, David, for the talk. Are there any questions? Let me check.
Oops.
Seems that not, but okay, it would be awkward that I ask the questions on Auger. But in any case, maybe can you actually explain how would the radio and the scintillators, just the upgrade would help in this muon problem? Exactly.
Sure.
Just as a short explanation.
Yeah, absolutely. So the scintillators, the fact that they have a different response to the electromagnetic and muonic component in the water Cherenkov detector allows us to deconvolve the contributions of the two particle types to the total signal. So for one measurement by a pair of scintillators and water Cherenkov detectors, we can estimate how large the signal from the electromagnetic component was and how large it was from the muonic component of showers on a station by station basis, as well as on an event level. So what we can do is we don't necessarily, or at least to complement these other hybrid methods described in this talk, such as using the electromagnetic profile prediction and such, we can have a separation of these components just from the surface detector to add depth, which can also give us an estimate of the composition of cosmic rays, hopefully a somewhat reasonable estimate on an event by event basis. But at large zenith angles, the scintillators aren't very effective because of their projection into the shower detector plane. They become very, very small at large zenith angles. So we plan to have radio antennas, which are sensitive to the pure electromagnetic component of showers. And as they're sensitive, these radio antennas, which will also go on top of the stations, to the pure electromagnetic component of showers. And for very inclined showers, you only have muons that arrive at ground. The water Cherenkov detector would measure the muonic signal. And there you could also do this separation of the magnitudes of these muonic and electromagnetic shower components, which would then give you, again, a separation of how large your hadronic component was versus your electromagnetic and facilitate these studies.
Okay, thank you.
Thanks.
Yeah. So I don't see any other questions. So it seems that everything was clear. Lukas, can you please share your screen and so our next speaker is going to be Lukas Zehrer, and he's going to speak about the multi-messenger studies with the Pierre Auger Observatory.
Hello, everybody. I hope you can hear me.
Would you also turn your camera on, or?
I don't have a camera on my office computer, sorry.
That's fine.
Okay, so my name is Lukas Zehrer. I'm from Austria, and I'm a PhD student at the University of Nova Gorica in Slovenia. Today, I will talk about multi-messenger studies with the Pierre Auger Observatory. I will start with an introduction about multi-messenger astrophysics. Then I will present some of the general main features of the Pierre Auger Observatory, an overview of the multi-messenger capabilities of the Pierre Auger Observatory is presented. The techniques and performances of searching for ultra-high energy neutrinos, photons, and galactic neutrons are described. And at the end, I will quickly talk about global networks before I finish with the conclusions. Multi-messenger astrophysics makes use of the messenger particles of all four of nature's fundamental forces. The earliest known messengers in the very high energies are the ones for the strong interactions. The messengers are cosmic rays, which were detected in 1912 by Victor Hess with his experiment in a balloon. For electromagnetic force, we observe photons. Messengers that communicate the weak interaction are neutrinos. And about gravity, we listen to gravitational waves. Here you can see a nice schematic view of different messengers traveling through the universe, where it is shown that neutral particles travel a straight line from their source, while charged particles are deflected by magnetic fields, or also interactions with the cosmic microwave background and other processes are shown. The datasets of interest of Auger for multi-messenger studies are less the charged ultra-high energy hadrons, since they're deflected from cosmic magnetic fields and therefore arrive delayed with a decreasing deflection with energy. But then we have the ultra high energy galactic neutrons, neutrinos, and photons. The Pierre Auger Observatory is located near the city Malargüe in the Mendoza province in Argentina at an altitude of approximately 1,400 meters. The observatory was completed in 2008. The Pierre Auger Observatory is the largest and most precise detector of ultra-high energy air showers induced by cosmic rays. On the left, you can see a sky view with just some of the most important parts, as there is the surface detector array that consists of 1,600 water Cherenkov detectors arranged on a triangular grid with 1.5 kilometer spacing over an area of 3,000 square kilometers, and an array of 61 stations with spacing of 0.75 kilometer over an area of 25 square kilometers. The surface detector array has a duty cycle of almost 100%. Moreover, the detector stations also provide a large aperture for inclined and upgoing air showers, a feature that is of key importance for the detection of neutrino-induced air showers. This 3,000 square kilometer array is overlooked by 27 fluorescence telescopes grouped in units of 6 at 4 locations on its periphery. Unlike the SD, the fluorescence telescopes are operated only during clear and moonless nights. That results in a duty cycle of 10 to 15%. This is accompanied by instruments for atmospheric monitoring, and currently the observatory is undergoing an upgrade called Auger Prime with the aim to further improve performance, which includes the scintillators on top of all the stations of the SD array, muon detectors, radio detectors. The SD stations sample the density of the secondary particles of the air shower at the ground and are sensitive to the electromagnetic, muonic, and hadronic components. The FD observes the longitudinal development of the air shower by detecting the fluorescence and Cherenkov light emitted during the passage of the secondary particles of the shower in the atmosphere. On the right here, you can see a schematic picture of the hybrid feature of the Pierre Auger Observatory. And combining these two well-established techniques has proved to be extremely rewarding in making it the most precise instrument to reconstruct the energy, mass, and direction of ultra-high energy cosmic rays. The advantages of this hybrid approach are the accurate energy and directional information, a low energy threshold due to the SD, and a small dependence on interaction models due to the FD. The disadvantage arises from the duty cycle of the FD. Neutrinos are the ideal messenger to study the high energy universe. They can travel in straight paths through the cosmological distance, unlike charged particles, which are deflected by cosmological magnetic fields, or photons, which are absorbed. They are a clear and direct signature of hadronic acceleration or interaction, and are capable of going through large meta depth without absorption. Besides all of that, they reveal information about composition of cosmic rays, the local environment at the source, and their evolution with redshift. The Pierre Auger Observatory is sensitive to neutrinos at energies greater than 10 to the power of 17 electron volts. Astrophysical neutrinos are created at galactic or extragalactic sources, which host cosmic ray accelerations. Example are blazars or gamma ray bursts. The flux of these depends on the energy spectrum of the primary particles and their production models, like in jets. Cosmogenic neutrinos are produced by ultra-high energy cosmic ray interaction with cosmic microwave background during propagation in the universe. Ultra-high energy neutrinos can be indirectly observed by the Pierre Auger Observatory. The idea is that since neutrinos have a very small cross-section, they can interact at any point along their trajectories in Earth's atmosphere, while the protons, photons, and nuclei always interact high in the atmosphere. Now, how can we separate the showers initiated by neutrinos from normal cosmic rays? The identification of neutrino showers can be performed only for inclined showers, where inclined means high zenith angle, considering the zenith angle 0 is in the vertical direction. For ordinary hadronic inclined showers, the electromagnetic component is absorbed in the atmosphere before reaching the ground. If a neutrino initiates a particle shower deep in the atmosphere, there will be a significant electromagnetic component of the shower, which reaches the ground level, as can be seen and compared on the right in the two pictures. In terms of observables, the digitalized signal traces recorded at the particle detectors are very sharp and short in the order of a nanosecond for a muon-dominated shower, which is all what can reach the ground from a hadronic inclined shower. This can be seen on the left in the middle plot. While as it is shown on the left bottom plot, the showers originating from inclined neutrinos that interact deep in the atmosphere, the signal will be spread in time over hundreds of nanoseconds due to the electromagnetic component of the shower that is, in this case, reaches the detector. Note that for vertical events, both the hadronic and neutrino-induced showers, the electromagnetic component reaches ground level and produces the same and indistinguishable signal as shown in the top left plot. With the Pierre Auger Observatory, we can identify neutrinos above 0.1 ex-electron volts in two ways. First, neutrinos of all flavors, means charged current and neutral current. They can interact with atmospheric nuclei and create a downward going shower. The neutrino surge is then performed for downward going low angle and the downward going high angle. And second, the Earth's skimming tau neutrinos at these energies, extreme energies with zenith angles, can interact via the charged current in the Earth's crust and produce a tau lepton, which emerges the atmosphere and creates an upgoing shower close to the ground. It's the most effective channel for neutrino detection is Earth skimming, because the target mass provided by the Earth is large compared to the atmosphere. The search for neutrino candidate events is performed separately for Earth skimming and downward going low and high showers. For the search for downward going events, the discrimination power is optimized with the use of the Fisher discriminant method, using a combination of several observables to optimize the separation between the background hadronic showers, called training data sample, taking a small period of real data and assuming them as a background, and Monte Carlo simulation neutrino events. For the Earth skimming analysis, one variable is enough to clearly discriminate, since there is no background in this channel. In the lower two plots, we see the distribution of the Fisher discriminant for data in the given time period versus Monte Carlo simulations. The value of the cut requires less than one event per 50 years on the full S-theory in the downward going high and one event in 20 years in the downward going low. Implication of the non-observation of ultra-high energy neutrinos yet are, of course, limits. Upper limits on diffuse fluxes and point-like sources. Here in red, we see the integrated and differential upper limit for the normalization constant, assuming an energy to the power of -2 flux for a single flavor for all the three channels. The dashed red line is the Earth skimming channel alone, which contributes the strongest to the limit. The shaded area and the dashed lines represent astrophysical and cosmogenic neutrino models. The limit is moving towards a scenario which then disfavors proton primary and strong evolution of the source with redshift, which means we are moving towards a scenario of mixed or heavy composition with weak evolution, which clearly implies a suppressed neutrino flux. It can be seen from the plot that the differential upper limit to the diffuse neutrino flux of the Pierre Auger Observatory is comparable at ex-electron volt energies to the limits given from ICECube. With the S-theory, we can detect neutrinos from point-like sources across the sky with peak sensitivities at declination around -53 and +55 degree. Since no neutrinos have been identified, upper limits on the neutrino flux from point-like steady sources have been calculated as a function of declination. In the plot, we can see the Pierre Auger Observatory's upper limits of a single flavor point-like flux of ultra-high energy neutrinos as a function of declination, together with ICECube and Antares. Note the different energy ranges for each observatory for this limit calculation. In the last few years, LIGO supplied us with several detection of gravitational wave events, like the mergers of compact binary systems, as there are binary black hole neutron star, and binary neutron star mergers. At the right side, one can see the 90% confidence level position contour for the very first gravitational wave event ever detected, together with the sensitivity sky areas for the Earth skimming and downgoing Auger field of view. This has been classified as binary black hole merger. Unfortunately, at the time of the event, in this case, there is no overlap with the field of view of the Pierre Auger Observatory. However, a significant portion of the position of the source was visible for a fraction of time in 1 day after the corresponding gravitational wave event, as the Earth rotates and the field of view of the Earth skimming and downward going high analysis moves through the sky. Since no neutrino candidates were observed from Auger in coincidence with this event, limits to the neutrino fluence are computed, which is directly related to the total energy emitted in ultra-high energy neutrinos, and is shown in the bottom plot. The blue shaded area is the 90% confidence level surface of the reconstructed source declination, illustrating the limited precision level achieved using just detection at 2 LIGO sites. The most restrictive limit of the total energy radiated in ultra-high energy neutrinos in this event is obtained for delta minus 53 degree. Here we see the gravitational wave event 170817 observed by the LIGO and Virgo detectors. It was produced by the merging of 2 neutron stars, and this is the first gravitational wave observation which has been confirmed by non-gravitational means. 1.7 seconds after the merger, a short gamma ray burst was independently detected by Fermi and Integral spacecraft. The aftermath of this merger was also seen by 70 observatories on 7 continents and in space across the electromagnetic spectrum, marking a significant breakthrough for multi-messenger astronomy. It was observed from radio to X-ray wavelengths over the following days and weeks, and was shown to be a fast-moving, rapidly cooling cloud of neutron-rich material, as expected of debris ejected from a neutron star merger. In the plot, in the bottom, you can see localizations and sensitive sky areas at the time of the gravitational wave event in equatorial coordinates. The gravitational wave 90% credible level localization in red, the direction of NGC 493 as a black plus symbol, and neutrino candidates within 500 seconds of the merger, and Auger's field of view for Earth skimming and downgoing directions. In the right figure, we can see that Auger provides the most stringent upper limit to the neutrino fluence at 90% confidence level in the range from 100 peta electron volts to 25 exa electron volts, complementary to IceCube and Antares. In a time interval of plus minus 500 seconds around the neutron star merger, its location was in the optimal Auger Earth skimming analysis window. Now we move on with photons at ultra-high energies. Ultra-energy photons, unlike neutrinos, have a limited horizon, ranging between a few 100 kiloparsec and few megaparsec in the energy range covered by Auger. Photons produce mostly electromagnetic showers with minor photonuclear or muon pair production. With respect to proton and nuclei, photons have a deeper shower development and a smaller muon content. As a consequence, they differ also in other observable characteristics like a steeper lateral distribution function, less triggered stations, a broader time front, and photons can also help to distinguish between scenarios of cosmic ray production, particle acceleration called bottom-up versus exotic models called top-down. Because of reasons of higher statistics, photon searches uses SD-only data. Variables with separation power are, for example, the rise time of the signal in an SD station, as shown in the figure, the curvature of the shower front, the area over peak, and others. These variables are then added and combined in a multivariate analysis. The most strong upper limits are provided using data from SD, which has a full duty cycle. The Pierre Auger Observatory is the most sensitive air shower detector for primary photons with energies above around 0.2 exaelectron volts. Using the surface detector array, photons in the zenith angle range from 30 to 60 degrees can be identified. The energy range covered in the search for diffuse photons is here extended about 3 decades, thanks to the very high exposure and to the analysis of data from the low energy enhancement of the observatory. Since neither the hypothesis of the candidate to be hadronic can be excluded, nor proven that the candidates are photons, a conservative upper limit on the photon flux at 95% confidence level is determined as shown in the figure, compared to model predictions and other experimental limits. The limit above exaelectron volt energies puts strong constraints on top-down models of ultra-high energy cosmic ray origin and on the most optimistic models of photon production from the interaction of protons with the CMB. Now we arrive at neutrons. Individual neutron-induced air showers are indistinguishable from those induced by protons. However, as neutrons travel in straight lines, a flux of neutrons could be detected via an excess of the number of showers from the directions of the shower sources. With this given neutrino decay lengths here, neutrons with energies of a few exaelectron volts can reach the Earth from the entire galaxy, but not from much further away. 11 classes of sources in the galaxy have been used as combined target sets for neutron searches with the Pierre Auger Observatory. These searches in the first 9.75 years of data taken by the observatory have yielded no significant excess. However, from the sensitivity to the target sources, 95% confidence level upper limits on the energy flux in neutrons have been deduced. In all cases, the limits already exclude energy fluxes on the level of the measured tera-electron photon energy flux from the target sets. These strong limits lead to the exclusion of an energy to the power of -2 Fermi acceleration of protons up to exaelectron energies, and also place strong constraints on ultra-high energy proton production in our galaxy. The Pierre Auger Observatory is contributing to global networks of observatories, like the Deeper, Wider, Faster program or the Astrophysical Multi-Messenger Observatory Network. Possibilities in such networks are to follow up, sending a trigger, or, as it is the case for Auger, both. Finally, let me quickly conclude with some key results. The Pierre Auger Observatory is sensitive to neutrinos, photons, and neutrons in exaelectron volts, and therefore is a multi-messenger detector. Auger showed to have an energy range for these messengers complementary to other observatories. String and upper bounds are placed on to a flux of diffuse cosmogenic neutrinos. Ultra-high energy neutrino follow-up searches were performed for LIGO-Virgo mergers. Auger provides the most sensitive ultra-high energy photon search over about 3 orders of magnitude, starting at 0.2 exaelectron volts, which set most stringent limits on the photon flux. And Auger's neutron limits are placing a strong constraint on ultra-high energy proton production in our galaxy. Thanks for your attention.
Thank you, Lukas. Any questions? Let me open the participants. It seems that people are shy to ask questions in the...
I have a question, but I cannot raise my hand.
Oh, okay, good. Go ahead, Marcus.
Hi, Lukas. Good morning. Very nice talk, and also congratulations on these results with Auger. So you showed the results on cosmogenic neutrino fluxes, and then also the ultra high energy photon fluxes. And of course, these are all related to the same model, cosmogenic production, or what is it is called here, GZK is also the cosmogenic. So it's interesting that the upper limits in both cases are basically touching these most optimistic proton models. So I'm wondering, from your personal point of view, are you expecting InnoG to first detect cosmogenic fluxes by the photon channel or by the neutrino channel, but in particular in view of future upgrades like Auger prime?
Maybe good question, what to detect first. I hope we detect both as soon as possible. I cannot predict what to expect first. That's I don't know.
And maybe one follow-up question. So for the neutrino channel, you're looking for horizontal showers, or in general for showers from horizontal directions.
Yeah.
Or upgoing. But for the ultra high energy gamma rays, are you in that case looking more for vertical showers?
For the photons in a zenith angle of 30 to 60 degree.
Okay.
And for neutrinos, we need these high inclined events, as I explained, because then we can distinguish them. Because here on this slide, for example, you see for vertical events, then you cannot distinguish if it was a neutrino or something else.
Yeah.
Yeah.
So you say 30 to 60 degrees would be...
For photons is optimum, yeah.
Okay, thank you.
Thanks.
So any other follow-up questions? Or if not, let's resume the first part of today. And we'll start as planned at 9:45 with the next talks. So now we are having a coffee break of a little bit more than half an hour. So see you all at 9:45. And for the speakers from the next session, so Valentina and the others, if you would like to test your sound and the sharing of the screens, please do so. And also thank you for all the speakers from this morning. Valentina?
Yes, may I test now?
Yes, please do so.
Oh, thank you. Are you seeing my screen?
Yes.
Okay, perfect.
Perfectly. Okay. We are also leaving the Zoom meeting, of course, open. So if you'd like to discuss and follow up questions for the speakers, you are more than welcome. And Zhili, Weng and Zhicheng, Tang, if you'd like to test your
Yes, this is Zhili. Good
okay.
morning.
Good morning. Would you also like to test your sharing of the screen, or?
Yes. So how about now?
Perfect.
Thank you.
That's perfect. Thank you. And Zhicheng?
Yeah, can you hear me?
Yes, very well.
Okay, so we'll try to share the screen. You see?
Perfect.
Okay, thank you.
Okay, thank you. So it seems that we are not going to have any technical problems in the next session. Okay, I'm gonna go to grab also some coffee, and we meet at 9:45. Okay, so I think we should slowly start. It's a 9:45 here. And in this set of talks, we have again 3 talks. And the first talk is going to be about precursors of poema on the use of SPB2. And the first speaker is Valentina. Valentina, can you please?
Yes, sure. I'll try to share my screen. Okay. Can you see it?
Can we also see you, or?
My connection is really bad.
Okay.
So usually I prefer to like have a good audio and no video.
Okay, thank you. That's fine. So you'll have around 20 minutes and 5 minutes of questions.
Okay, thank you.
Thank you.
So, good morning, everybody. I'm Valentina Scotti from University of Naples and INFN of Naples. And today I'm going to talk about the use of SPB2. Use of SPB2 means Extreme Universe Space Observatory on a superpressure balloon. And this is a precursor mission for future space observatories for multi-messenger astrophysics. The idea is to use the Earth as a giant particle detector, studying from the edge of space fluorescence and Cherenkov light coming from ultra-energy cosmic rays, but also from tau neutrino background. This mission is part of the effort of the GEMUSO international collaboration. This is a collaboration of 350 researchers from 16 countries, and the scientific case has been positively evaluated by several national and international space agencies, and funding for the detectors and precursor mission are ongoing in all the participating countries. The approach of GEMUSO is to study from space transient luminous phenomena in the Earth atmosphere, to start astronomy and astrophysics through the particle channel with a specific target at extreme energy cosmic rays, which are at energy above 10 to the 19 electron volt. Just for a comparison, we are well above the energy reachable with the man-made accelerators. The main science objectives are the identification of extreme energy cosmic ray sources, the measurement of the spectra from individual sources to constrain the spectral shape, the flux, and the power exponential, to understand and constrain both acceleration and emission mechanism. The main challenge at this energy is the extremely low flux. So far, only around 60 events have been detected, and the sources are still unknown, even though they are thought to be extragalactic. The scientific goal of GEMUSO will be achieved studying from above both Cherenkov and fluorescent light generated by showers created by cosmic rays. The shower appears on the telescope as a faint track moving at the speed of light. In this plot here, you can see the number of photons at the detector for a shower of 10 to 20 electron volt. The typical shower development lasts around from 10 to 100 microseconds. And since the photon flux is very low, the fluorescent light can be detected only during moonless clear nights. The main advantages of space observation are that the target volume is far greater than it's possible from ground, and this gives a huge improvement in statistics, and that we can have full sky coverage. The GEMUSO program to study ultra-energy cosmic rays from space includes different experiments which use the fluorescence detector to make proof principle of the extreme energy cosmic rays observation from space, and also to raise the technological level of the instrumentation to be employed for future space mission. USO SPB2, the main focus of my talk, is built upon the USO SPB1 experience to pave the way towards the POEMMA mission. USO SPB1 was a NASA ultra-long duration flight, which was launched from Wanaka in New Zealand in 2017. The goals were to measure a fluorescent signal from showers, measure the ultraviolet emission over the ocean and over clouds, so the background, and to search for ultraviolet signature from other objects. The target flight duration was 100 days, but unfortunately the balloon developed a leakage and the flight was terminated after only 12 days. Thankfully, during these days, the detector performed well and it was stable, so at least we had a technological proof. Most of the data were downloaded before the detectors sink down in the Pacific Ocean, and we could measure both the ultraviolet emission and direct cosmic rays hitting the camera. Unfortunately, in the time we were floating, we couldn't detect any ultra energy cosmic rays. USO SPB2 represents also a step toward the POEMMA mission, which is designed to observe both extreme energy cosmic rays and cosmic neutrinos with an unprecedented sensitivity. The design of POEMMA builds upon the design of WALL and the development of the USO collaboration, and also the idea of the Shunt Observatory. POEMMA is a set of twin photometers flying in tandem to monitor the Earth's atmosphere during the night. It will study extensive air showers, but also neutrino. And the stereo, it will operate in stereo observation in two modes, pointing at the nadir and at the limb. And in both modes, it can monitor a huge volume of the atmosphere to discover the origin of this most energetic messenger of the universe. And you can see that even though it will be launched in 2030, it will be competitive and it will represent a huge improvement in the sensitivity. The POEMMA is designed to have a hybrid focal surface and a Schmidt telescope. The idea to use a Schmidt camera is to obtain a wide field of view without chromatic aberration. The hybrid focal surface is designed to detect fluorescence light with the multi-anodic photomultipliers tube with a 1 microsecond sampling, and Cherenkov light with a even faster detector based on silicon photomultipliers. And while the fluorescence detector will look directly on ground, the Cherenkov detector, the part will look at the limb of the Earth. The basic unit for the fluorescence detection is called the photodetector module, and each basic unit consists of around 2000 pixels, while the basic unit for the Cherenkov detection is based around a unit of 500 pixels. In order to be a step toward POEMMA, USO SPB2 will host on board 2 telescopes, and this is a difference from all the previous Pathfinder mission in the USO program. The fluorescence detector is based on multi-anodic photomultipliers, and it builds on the experience of USO SPB1 and is designed to detect ultra-energy cosmic rays. The other telescope measures the direct Cherenkov visible light, and the second photodetector is made of silicon photomultipliers. The system is also completed by several ancillary devices. The main goal of this mission is to detect fluorescence from above to confirm the expectation of observatory working on the ground. And this mission will have a lower threshold and a larger acceptance compared to the one of USO SPB1. In addition, this detector will add new unexplored areas, and it will be able to detect Cherenkov light from cosmic rays and to measure the background for upgoing tau decays from cosmogenic neutrinos. From a technological point of view, this mission will be a test for the instrumentation and methods for POEMMA, and this will be the first telescope to use Schmidt optics in space. The floating altitude of the mission is 33 kilometers, and hopefully the duration target is 100 days. The payload mass is slightly above 1 ton. In this slide, I summarized the main specification of both the telescope. You can see that they have a different energy threshold, around 5 times 10 to the 18 for the fluorescence detector, electron volt for the fluorescence detector, and around PeV for the Cherenkov detector. Of course, the wavelength sensitivity is different because we are looking at 2 different phenomena, and for the same reason, also the time unit is different. Once again, I want to stress that while the fluorescence telescope is pointing down, the Cherenkov telescope will look at the limb. The 2 telescopes share the same mechanical structure, mirror, and corrector plane units, and both have a 1 meter diameter of corrector plate. The fluorescence telescope, as we saw in a previous slide, has a focal surface based on multi-anodic photomultipliers. And the main difference with respect to the USO SPB1 are that here we will have 3 photodetector modules compared to 1 of the previous mission. And in the previous mission, we used Fresnel lenses, but this time we are going for a Schmidt optical system. The signal coming from the photomultipliers are read out by a specific ASIC, which is followed by multiple trigger levels to filter out the noise and identify a level of interest. The whole system has a single photoelectron counting capability in order to detect the very faint fluorescence signal. The peak energy sensitivity for the fluorescence detector is around 6 times 10 to the 18 electron volt, and we expect to collect a ultra energy cosmic ray event every 13 hours. So for an 80-day flight with 15% of duty cycle, we expect around 20 events. And if we are lucky and we have a flight similar to the one that we had in 2017, we expect to collect at least 3 events. So the performance will be increased at least for a factor 3 with respect to the previous mission. Of course, the trigger optimization is still ongoing, and our pre-flight expectation will be refined while the instrument is assembled and tested. The Cherenkov telescope focal surface is based on silicon photomultipliers, and Also in this case, we will have a Schmidt telescope, but the difference is that here we will have a bifocal mirror. This kind of mirror allows to distinguish between a charged particle hitting the camera, which makes only one spot, and a signal coming from far outside the field, the detector, which will make two spots on the focal surface. In this case, the readout is based on the ICHEP, and the readout speed is around 1 mega sample per second. The Cherenkov telescope aims at measuring the background for the flux of low energy tau leptons, and there are papers saying that you have a significant flux at low energy for this kind of emerging tau, and USPB2 will be able to sample up to angle of 10 degrees coming out, as you can see in this, with geometry that is depicted in this slide. And once taken into account the atmospheric transmittance, the Cherenkov telescope still looks capable of detecting the Cherenkov signal generated by upgoing tau. The system is completed by several ancillary devices. We will have a NELT-led system to check the camera health and response, 2 atmospheric monitor for an independent measure of the night sky background in the ultraviolet range, and 2 Hammons to verify the dark condition inside the telescope in order to avoid to damage the telescope. Then an infrared camera will monitor clouds and measure their altitude, and this is a necessary measurement to evaluate the flux for the fluorescence telescope. The launch of the USPB2 is planned for 2022, but of course to get there we need to hit several milestones on the road. We are we have some delays, but our aim is to have some field test campaign at the end of the assembly and after the thermal vacuum chamber test. This test will be held in the Utah desert, and they will give us a calibration of the detector response, and they will be useful to fine-tune our trigger algorithm. So we are really looking forward to this test, and this is something that we want to do before saying that we are mission ready. Going more in detail about the current status of the mission, we are here at the moment. So the optics are being fabricated, and the multi-anodic photomultipliers will be delivered at the end of the summer. Of course, our situation was complicated by the current pandemic because this is an international effort, so we had to deal with international travel and international shipments. At the moment, the DIAQ fabrication is completed and tests are running. The fabrication of the photodetector module has some delay, but it will be done by the end of the year. So probably we have 3 to 4 months of delay. And currently we are looking for facilities for thermal vacuum tests, which will be probably held during the next winter. To summarize, we had a successful launch of USPB1 in 2012. Most data were downloaded and despite the premature termination, and our detector performed well. It was stable and it was able to measure the background ultraviolet emission. USPB2 will be an improved 2-telescope instrument built upon the experience of the first SPB mission. but it will also add some new unexplored areas, such as the Cherenkov detection and the neutrino background. The launch is planned for 2022. And this is a scientific and technical pathway toward POEMMA, which is a space mission which will open 2 new cosmic windows, both neutrino from astrophysical to cosmogenic and extreme energy cosmic rays. Thank you.
Thank you very much, Valentina, and wish you good luck with building the detector in this period.
Yeah, we need that. Thank you.
Yes. So, are there any questions for Valentina?
Can I ask
Marcus? Yes, please go.
Yeah, sorry, I raised my hand here. I wanted to ask about angular resolution. What do you think can you resolve in terms of the arrival direction of, in particular, neutrinos, if you want to do points for studies?
Okay, for the neutrino, we have our field of view is around part of the degree, and the angular resolution it also depends. The number are not fixed yet because it depends on the tilting angle. So we will look at the limb, but we have not yet established the precise angle. But I mean, we are not going for detection of neutrino, but because we won't have enough. Our field of view is not big enough, so we are going mostly to measure the background and to prove that the concept can work.
But for the final POEMMA mission.
For POEMMA.
Yeah.
For POEMMA, okay. I think it's tricky to say because here it's even less defined, but there are we are finalizing our simulation, and I think that next year we will be out with some paper with more precise numbers.
Okay, thanks.
I see no hands raised, but Valentina, I have also a question.
Mm-hmm.
I didn't understand why for the Cherenkov you are using a much finer binning for the time than for the fluorescence.
Because the time...
And coming to that, is like if you have the... Are you measuring the direct Cherenkov light or...
For the Cherenkov telescope, yes, we are measuring the direct Cherenkov light, while in the case of the fluorescence, we use some Cherenkov light, but only to mark the like our event, because it arrives at the end of the fluorescence light. And the reason why we have 2 different time beams is because these phenomena occur at totally different time scales. So we need to have different detector for that reason.
Yeah, I just wondered because 1 microsecond for the fluorescence.
For the fluorescence, because you have...
Isn't it too large? Doesn't it affect the resolution that you're going to have on other variables like X marks or this kind of things?
No, because the development of the shower seen from high altitude has a time span of around 100 microseconds. And with the resolution of 1 microsecond, we are able to see all the evolution of the track so that we are able to really distinguish an event, a cosmic rays event.
Okay, thank you. Some other questions? No. But actually, I have one extra question. So you're saying that for the new mission, you have exposure or sensitivity that is a factor of 3 larger than from the previous flight. And what is the main change that increases this
that
exposure?
we have 3 photo detection modules instead of 1. So our field of view is like 3 times the previous one.
Okay, thank you. So there are no more questions, I think. So let's thank Valentina again, and the next speaker is, 1 second, it's Zhili Weng, and he's going to tell us everything about where the positrons are coming from in cosmic rays. So please start.
Yes, can you see my screen?
Yes.
Okay, so hello everyone. I am Zhili Weng from MIT and from the AMS collaboration. So today I will share with you the precision measurement from AMS on cosmic ray positron and electron. Let me put my pointer. Yes, much better. So there are different sources of cosmic ray electron and positron in the galaxy. Electron can be accelerated from supernova remnant together with proton, helium, and other primary cosmic rays. During their propagation in the galaxy, some of the proton and nuclei may interact with the interstellar medium and produce a secondary positron and electron in a small amount. New astrophysical sources like a pulsar may produce primary source of positron and electron at high energies. More interestingly, annihilation of dark matter particles may also produce positron electron, which will imprint a signature in their energy spectrum, and therefore precision measurement of their spectrum may reveal new physics phenomena in cosmos. These are very difficult measurement because you need to separate the charge and distinct the signal from the huge background. And these are the results before AMS. They often have a large uncertainty and may not agree with each other. This limits the understanding of their true behavior. AMS can accurately measure positron and electron up to a few TeV. The tracker and the magnet are the core of AMS. The single point resolution for a charged 1 particle is at 10 micron, and the tracker measures the sign and the magnitude of the particle, and therefore distinguish between positron and electron up to a few TeV. The strength of AMS detector is that by combining the independent measurement of momentum by the tracker and the energy measurement by the ICHEP, we can identify positron from proton by looking at the matching between energy and the momentum. For example, in this plot, electron and positron are equal or larger than 1 in the electron momentum matching, and while proton have much less energy compared to momentum. At high energy, electron may be measured as positive in the detector, and we define this as charge confusion background. Charge confusion occurs due to large angle scattering in the detector or from interaction with the detector material. In our analysis, we identify and measure directly from the data the level of charge confusion using a dedicated charge confusion estimator. And to identify positron from a large background of proton, we rely on 2 key subdetectors of AMS. The transition radiation detector on top identifies positron from proton using transition radiation. We combine the 20 layers proportional tube signal into a TRD estimator. And the performance of this estimator is shown on the right as a function of momentum. At large energy, the separation power at a large energy range, the separation power is maintained above 1 part in 1,000. And starting from few hundred GeV, proton starts to emit transition radiation photon, and therefore you see a drop in the rejection power. However, in the analysis, you can always relax the requirement in the efficiency in order to gain back some of the rejection power. On the bottom is the electromagnetic parameter. It has 17 radiation length. It measures the energy and the 3-dimensional shower development of positron and electron. And together with the tracker, the ICHEP proton rejection power is above 1 part in 10,000 in nearly entire energy range. So what is more important is that TRD and the ICHEP are separated by the magnet. and therefore they have independent particle identification capability, such that their combined rejection reach over 1 in a million. So for each energy beam, the number of positron and the electron are obtained from a fit to the data in the TRD estimator and the charge confusion estimator two-dimensional plane. This method allows precision determination of the signal and the background. So here is an example of the fit around 500 GeV. On the left is the projection to the TRD estimator axis. The positron signal in red are separated from the proton background. On the right is the projection to the charge confusion estimator axis, where the electron charge confusion background are clearly separated from the positron signal. And for the analysis that we just published last year, we have obtained 1.9 million positron from energy range up to 1 TeV and 28.1 million electron up to 1.4 TeV. We have performed detailed systematic error analysis and exhaustive cross-check with different methods to ensure the accuracy of our measurement. The electron charge confusion background is less than 8% at the highest energy beam. This is measured directly from data and is in good agreement between Monte Carlo and data. We have also verified that the measurement is stable over a wide range of selection. For example, we can reduce the ECOW selection efficiency to 65% and improve the proton rejection by a factor of 3, while we check that the positron flux result is still in the same level. Another important systematic uncertainty is the energy scale. The uncertainty in the absolute energy scale of the AMS ECOW is at 2% up to 300 GeV as verified by the test beam, and increased to about 2.5% at 1 TeV. The measurement accuracy are currently limited by statistic uncertainty, and therefore by continued data taking, we will be able to improve the accuracy of the data and extend to higher energy. So this is the latest AMS result on positron and electron, just published last year on Physical Review Letters. These results reveal complex energy dependence of positron flux and of electron flux. Let's first look at the positron spectrum. The positron flux is scaled by energy to the third power for display purpose only. The positron spectrum in this scale exhibit a distinct energy behavior. So starting from few GeV, it starts to flatten and followed by a rise or excess of positron, and then followed by a significant drop off above 300 GeV. The complex energy dependence of this positron flux can be studied by looking at their spectral index. The spectral index is defined by just d log phi over d log e. So as shown here, the positron spectral index is not a constant. Start from 7 to 25 GeV, the spectral index is about -3, and this increased significantly to about -2.7 in the energy range, corresponding to the excess. And after that, it starts to decrease, reaching to below -3 above 300 GeV. So to determine the transition energy, we feed the data to a broken power law, shown here. First, we found that starting from 25.2 GeV, there is a significant excess of positron compared to the low energy trend. And this excess is quantified by this delta gamma, which is found to be over 6 sigma. Similarly, a fit to the higher energy range shows that starting from 284 GeV, there's a significant drop off with 3 sigma significance. So this distinct behavior of the positron flux cannot be explained by a traditional cosmic ray model. Indeed, if we compare the positron flux to a secondary positron production from standard astro-particle physics models such as Gauss probe, we can see that the positron flux by far exceeds the prediction from collision of cosmic ray. And therefore, the excess of positron starting from few GeV may require a primary source of high energy positron. So we have determined that the positron flux can be described by the sum of 2 components. The first component is associated with cosmic ray collision at low energy, and the second component is associated with a high energy primary source. At low energy, the positron mainly come from secondary production. Here we compare the low energy contribution, which is the data minus the source term, and with that from 2 predictions from Gauss probe. As seen, the behavior of the low energy part agree qualitatively with the prediction from secondary collision. And given the large uncertainty, we will say this is qualitatively in agreement. And at high energy, the source term dominates the positron spectrum. A distinct feature of the new source term is the exponential cutoff ES. The AMS result shows that the cutoff energy ES at infinity is excluded at more than 4 sigma, and the cutoff energy is evaluated to be about 810 GeV. The origin of this high energy positron can be from dark matter collision or astrophysical object like a pulsar. As illustrated here, the AMS result appear to agree with a dark matter model with dark matter mass 1.2 TeV. However, currently there are still large uncertainty in the data at high energy, and we need to improve the measurement such that we can ascertain the exact behavior after the cutoff. High energy positron may also come from astrophysics object like a pulsar. Pulsar are just fast rotating neutron stars with a dense magnetic field. Light rays can convert into positron-electron pairs and may be accelerated to high energy in the pulsar wind nebula. However, pulsar cannot produce proton-antiproton due to their high mass. So as Dr. Tang will present after me, the AMS measurement of positron and antiproton is quite interesting. Starting from 60 GeV, the positron and antiproton show surprising similarity in their energy spectrum. And this is quite curious observation. So it may indicate a common origin of antiproton and positron in the cosmos. And if this is the case, then the high energy positron most likely is not originated from the pulsars. A point source like a pulsar will also imprint an observable anisotropy in positron incoming direction. As my colleague already presented in the Tuesday, today the AMS measurement of the positron arrival direction is consistent with isotropic. And by continuing data taking to 2028, we will reach a sensitivity for positron dipole anisotropy of 1%, which is expected from some of the pulsar model. Another class of model predicts that astrophysical source like a supernova remnant may also accelerate secondary particles. Currently, there is not a model that may simultaneously expand the wealth of the AMS measurement. For example, model parameters that is tuned to match better with the positron data may not fit with the secondary to primary flux that is measured by AMS and vice versa. And we think that the precision measurement from AMS on primaries and on secondary nuclei, together with antiproton and positron electron anisotropy, can all help to distinguish and constrain different origin of positron. And for AMS, what is most important is to continue collecting data through the lifetime of the space station. This will allow us to significantly improve the accuracy of the measurement and go to beyond 1 TeV. For example, it's illustrated here, we will be able to measure the positron behavior above 1 TeV and improve the accuracy below. On the other hand, electrons behave very differently from positrons. This is the latest measurement from AMS on cosmic ray electron with 28.1 million electron events, just published also last year. The electron spectrum also exhibits a complex energy dependence. The spectral index of electron is also not a constant, as shown in here. Starting from 20 GeV, the electron spectral index starts to harden, and then it becomes nearly energy independent above 56 GeV. A fit to the data using the same broken power law reveals also a significant excess of electron compared to the lower energy change. So this significance of the change is again quantified by this delta gamma, which is found to be 7 sigma away from 0. And we have found that this change occurs at around 42 GeV. And above 42 GeV, the electron flux can be described by a single power law. So this is the fit to the single power law in green. And we see that contrary to the positron flux, the electron flux do not show an exponential cutoff in the data for the moment. And the data show that an exponential cutoff like the one in the positron flux is excluded by more than 5 sigma, below 1.9 TeV. The origin of cosmic electrons are quite different than the origin of positrons. So first, most of the electrons are not produced from cosmic ray collision, as indicated by this green field area here. So most likely there are primary source of cosmic ray electron for example, from supernova remnant together with proton, helium, and other primary cosmic rays. And at high energy, if there is a primary source like a dark matter, they may produce the same amount of positron and electron. So one can expect the same source contribution, just like the one from the positron source term. And therefore, we try to fit the electron flux with a single power law, plus the same source term obtained from the positron fit. And we have found that for the moment, the electron flux is consistent with a charge symmetric source term as shown in this upper right plot. But simultaneously is also consistent with just a single power law without any source term contribution. And we hope that future AMS measurement with improved accuracy and energy reach may reveal more detailed feature in the electron spectrum itself. We also found that in the entire energy region, the electron flux can be described by two power law functions. Currently, for example, at low energy is power law A, and at high energy it starts to transition to another power law. And currently there's no definitive answer on this changing behavior of the electron spectrum. This may suggest there are different sources of electron from discrete nearby supernova remnant, or may reveal new propagation effect of electron and positron in the galaxy. So this brings me to the conclusion. AMS performed precision measurement of the positron flux to 1 TeV and the electron flux to 1.4 TeV. The positron flux shows distinctive energy dependence, where significant excess starting from 25 GeV followed by a drop-off. The positron flux is well described by the sum of a diffuse term and a new source term with a finite energy cutoff at 810 GeV, with a significance of more than 4 sigma. These properties suggest a primary source of high energy positron. On the other hand, the electron flux also exhibits a significant excess starting from 42 GeV, but the nature of this excess is different from positron. And the electron flux does not show an exponential cutoff. This suggests that most of the high energy electron originate from a different source than the high energy cosmic positron. And looking into the future, by continuing the measurement through the lifetime of the space station, currently planned to 2028 and beyond, AMS will improve the accuracy and extend to high energy, and we hope to determine the origin of high energy positron and electron. Thank you for your attention.
Thank you very much for your talk and for keeping on time, and also for this very interesting results. So are there any questions? Thomas, Marcus, usually if you want to ask something, just speak up. But I don't see any questions. Let me check the uttermost. Okay, so actually I do have a question. So if I understand properly, what you would need to search for, how you could disentangle between this pulsar origin and dark matter origin would be searching for the anisotropies. Is this correct? Or is there some other way of looking at this? Because I didn't properly understand this relation between the positrons and protons.
Yeah, so first, as you correctly pointed out, the anisotropy is a great channel to look for the disentangling different model. And the other thing is that if it's really from a dark matter around 1 TeV, then we expect that above 1 TeV, the positron flux level will significantly drop down to the collision secondary positron, which is very close to non-existent. So if it's from pulsar, then this drop-off may be less prominent, or if there's multiple pulsar that is contributing simultaneously to the positron, then you may expect another feature or another bump or another excess at high energy, just due to different age of the pulsar, etc. So this is also another possibility. And then the third is, as you said, the similarity between the positron and the antiproton. So there's still many explanations. But the one thing that can be certain is that if positron and antiproton is from the same source, then it cannot be from pulsar. So that's the areas that we'll be looking into.
Okay, thank you. That's, now it's much more clear. Any other questions? It seems that not. So thank you very much for the talk, and we are going to switch to the antiproton flux now. So I would like to ask the next speaker if Zhicheng, I hope I pronounced properly the name.
I'm here.
Okay.
You can see the screen?
Yes, very well. So please go ahead. As usual, I have 20 minutes plus 5. So,
okay, so
go ahead.
I'm going to present the antiproton flux and the properties of elemental particle fluxes in primary cosmic rays measured with MS on behalf of the collaboration. I'm Zhicheng from the Institute of High Energy Physics, Chinese Academy of Science. So the 4 elemental particles, proton, antiproton, positron, and electron, they live long enough and can travel through the whole galaxy. So they carry information of the origin of and the propagation history of the cosmic rays. The protons and the electrons are mainly believed to produce and accelerated in supernova remnants and together with other cosmically primary components. And this particle also interact with interstellar medium and produce secondary components, including the antiparticles, antiproton, and positrons. New sources like dark matter will produce particles and antiparticles in equal amount. So measurement of the antiparticles would be more interesting because they are less abundant in the ordinary cosmic rays and easier to find the new physics. The comparing of the properties of flux of these particles is a major tool to look for new physics in space. As a unique magnetic spectrometer in space, different particles, either matter or antimatter, will have different response in MS independent subdetectors. So cosmic rays are measured up to TeV range simultaneously in the same detectors. It's an unprecedented data sample to study the properties of elemental particles in cosmic rays. As one of the key detectors in the measurement, the tracker have 9 layers of silicon detectors. The first on the top of TRD, and the last between rich and the ECA. And the other 7 layers are surrounded by the magnet with field strength 1,400 Gauss. The single point resolution of each detector is better than 10 micron, and after calibration, this center value is stable with time. This bottom right plot shows the tracker heat residual in the first and the last layer of tracker, and it's quite stable within years, and the sigma is only 2 micron. With the 3 meter level up from first to last layer, we are able to measure the momentum of the charge 1 particle up to 2 TeV. The transition radiation detector is used to separate electron positron from proton and protons. It consists of 20 layers of proportional tubes interlaced with the Flux radiator. When the proton and proton pass through the ionization signals, and while the electron and positron will emit additional transition radiation and leaves larger signal in the tubes, as shown in the bottom left plot. Finding the information of 20 layers, we are able to achieve a particle identification power levels of 1,000 to 10,000. Before launching to space, we have done extensive calibration of the MS detector at certain test beam with different particles at different energy and different positions and angles. With the comprehensive understanding of the detector, we are able to precisely simulate the response of the detector. As shown in the bottom right plot, this is a tracker rigidity resolution function comparison between Monte Carlo and data. It shows a very good agreement, at least 5 order of magnitude, not only in the core region but also on the tails. So that the unique properties of MS is able to calibrate the detector also in space beyond the test beam energy. So in the left plot is the verification of Monte Carlo with proton above TV. And the right plot shows the measurement of the absolute rigidity scale with the cosmic ray electron and positron samples. And the accuracy of the rigidity scale is found to be only 0.033 inverse TeV, and the content with time is only limited by the positron statistics. So with this precise measurement, this is our latest proton flux shown in red, based on 1 billion protons. The results show a progress hardening about 200 GeV, and the agreement with our previous publication. Now here is the antiproton analysis. Antiproton flux is only 10 to the -4 of the proton flux. So a percent precision measurement will require background rejection close to 1 in the millions. We use TRD, top and ridge, to select the downgoing particles and measure the velocity, and the TRD and ICHEP are used to reject the electron background. And most important, the tracker measures the rigidity and rejects misidentified protons. The right plot shows an example of the 363 GeV proton events in the MS detector. Finally, more than 500,000 antiprotons are selected in the analysis between 1 and 525 GeV. This is an example of antiproton identification at about 6 GeV, where we use RICH and TRD to identify antiprotons. So we can see different species very clearly, and the antiproton signals are well separated from the ion and electron background. At high energy, it's very important to ensure the charge sign of antiproton is correctly measured in the tracker. So some protons with scattering and intact antigen will be seen as antiproton in the detector. So the information from tracker and time plot are used to build a charge consumption estimator to reject the misidentified proton as shown in this plot, well separated from the antiproton signal and the charge consumption from background. Then a two-dimensional template fit are used to extract the number of antiproton signals in the high energy region. The left plot shows the projection of the fit on the TRD estimator plan, and the right plot is projection on the charge consumption estimator. The black points are the data, and they fit well with the templates, and also the antiproton peak is clearly visible. We have identified more than 3,500 antiprotons above 100 GeV. While before MS, there are only 3 events in cosmic rays. To match with this statistics, we have done extensive systematic studies. As mentioned in the method in our previous communication. So this is the result of the antiproton flux shown in red, and comparing with the proton flux in blue. So you can see that above 60 GeV, the antiproton and the proton have identical spectral behavior. we take the ratio of the antiproton flux, we also show no rigidity dependence about 60 GeV. A fit to a power law in the range of 60 to 525, which shows that the difference between the power law index of proton and antiproton is consistent with 0. So there's no rigidity dependence. After our first publication of antiproton results, there have been many discussions on the origin of high energy antiprotons. In recent years, the accuracy of the secondary production and proton calculation have been improved, and the discussion continues. On many theoretical models, we have shown some recent modeling, including only secondary production of antiprotons. And compared with the measurement in red point, these different curves are different models. The upper panels are the antiproton flux, and the lower is antiproton flux ratio. These models only consider the secondary production of antiprotons, and also there on this page is other models, including also in contribution from the dark matters. So you can see that a lot of attraction being focused on the contribution of antiproton at around 20 GeVs, while actually the largest discrepancy exists on both high energy end and also low energy end. With further MS measurement, including maybe also the time-dependent antiproton flux, it may help the understanding of the origin of the antiproton. So this is our recent publication on the electron and the positron flux based on 28 million electrons and about 2 million positrons. That have just been presented in Zhili talk. So now the electrons and protons, they are the most abundant elemental particles in cosmic rays, and they are considered mostly primary components. The comparison of the protons and the electron fluxes shows distinguishingly different behavior. So the proton flux can described by the precursor hadronic power law, and the electron flux is a sum of two power law components. And that the electron flux decreases faster, much faster than the protons, which is usually attributed as anti-Gauss effect in the propagation. But trying to find that the spectrum of positron and the proton flux are very similar, about 60 GeV to about 300 GeV. And above 300 GeV, the positron start to show a sharp drop off, and proton flux actually decrease with energy lower. Another surprising observation is that the positron flux, the spectrum is harder than proton spectrum, low energy of 260 GeV. This plot shows the ratio of positron flux and the proton flux, and fitting to a broken power law shows that below 260 GeV, power law index is positive. So it's already a clear indication that the positron cannot be pure secondary production. Also, very interesting to see that the spectrum at high energies, the antiproton and the positron also have very similar behavior. This suggests a common source of high energy positrons and antiproton, but it cannot be pulsars because due to the high mass, the pulsar cannot produce high energy antiprotons. And it's really interesting to see that the flux ratio of positron and antiproton is constantly about 2 in large energy range, from 50 to 500 GeVs. So let me summarize the properties of elemental particles are being measured and compared in MS, and in a large energy range, this positron, proton, and antiproton flux show similarity in the spectrum behavior. So MS is exploring fundamental physics in space with many different types of cosmic rays. And many new and exciting phenomena are observed already. And by tracking data through the lifetime of the space station, MS will greatly improve the accuracy of this measurement and will reach to higher energy. So, for example, for the prediction of measurement in 2028, we can have more to reach to higher energy, better accuracy. So that's all. Thank you.
Thank you very much for the talk, and also for showing these very nice results. Are there any questions?
I have a quick question.
Please go ahead, Marcus.
Thank you, and congratulations on these results. On slide 15 and 16, you show a comparison of fits where you also include I believe a 10 GeV dark matter model on slide 16. I was wondering, can you say something about the significance of this fit? I mean, how much do you improve your background only fit when you include this additional contribution from dark matter?
Well, this is actually taken from many publications, so they are different. So the contribution here is actually not very big compared to the traditional secondary production, I think.
Yeah, I was wondering how significant you can. I mean, you have very precise measurements in the AMS data. If you look at the flux, so I was wondering if this is also reflected in a high delta chi-squared or alternative statistical measures.
Yeah. So, but I don't have the actual number of the significance. Sorry.
That's all. Thank you.
Okay, thank you. So, are there any other questions?
Yeah, so if I can comment on the previous question.
Please.
So yeah, the different authors have predicted, have got a different result on the significance. But if my memory is right, it's all about 3 to 4 sigma. And I think you are asking about whether the inclusion of the correlation matrix from the experiment side will improve this significance.
So yeah, thank you. You say 3 to 4 sigma for this excess?
Yeah, that's what I remember from some of these reference. And some author claims that if the correlation is taken into account, then may boost some of the significance. But yeah, from us experimental point of view, we just aim to provide the most accurate data, and then yeah, the theory community may take the best advantage of all this measurement. So this is not our fit, it's just taken from some reference.
Thank you.
Okay, I don't see any hands raised, but maybe can I ask also a question about the significance? This is again maybe for both of the speakers. For the positron flux, this turnover, this change in the power law, the highest rigidity. Is it which is the significance for this flux drop, change from 2.7, or how much was the spectral slope? So exactly here, if we go here and any of the positron fluxes, so it, around this drop in the flux.
Then go to the slide with positron and the proton.
Yeah, but so this is not this is a prediction, but here.
So
not this one, just this one of the slides. Next slide, maybe.
The one with
here. One before here. So this turnover at around a few hundreds of GeV.
Yeah. So for the positron, if you fit in a model independent way, for example, just exponential, just power law, then the significance is about a bit more than 3 sigma. If you take into account both contribution from low energy and high energy, then the exponential cutoff significance is 4 sigma effect. So you can imagine without the cutoff, the positron spectrum will continue to go up.
Good, thank you. I was just wondering because of this power loss, the steep power loss, it's really not trivial to get this efficiency. So, and if it's 3 sigma only from the data, that's very nice. So, any other question? No, it seems not. So let's thank again the speakers of this session. And we will have now again a coffee break. And after the coffee break, we will resume as scheduled at 11:30. And then we are going to switch to Baikal and neutrinos. And as usual, I would like to ask the speakers from the next 3 speakers if they can test their audio and their sharing of the screen before the session would be very nice.
Hi, can I test the sharing?
Yes, let's do so.
Is it okay? Do you see it?
Now we see it in the, but not as a full screen.
Like this?
No, it usually does not work like this. So, principally, you should, if you want to switch like that, you have to share the full screen and then move to the full screen mode, because otherwise it remains the small window.
And here now?
Now it's perfect.
Thanks, sorry.
Okay, thank you. Okay, and then Tommaso already changed, and then only Grigory if he wants to try. Grigory, would you like to try the sharing of the screen and the audio?
So can you hear me?
Yes, very well.
Okay, very well. Let me try. Just a second. Okay, can you see the screen?
Yes.
Okay, let me try to open that up. Yeah, can you see the talk?
Yes, but we're just still having the Zoom window, like blocking part of the
I see.
Standard Zoom problem. Yeah,
okay. So should I try something else? Or?
It's fine. That's perfect. Okay, thank you.
Thank you.
Let's meet in at 11:30. So enjoy your
Joanna.
Yes. Tommaso, yes.
Can I try again? Can I try again to share my screen just to make a test, if I may?
Just a quick.
Do so, yeah.
Okay. You should see. Okay. Okay.
Yes.
So
it's
this
fine.
is okay. Okay, good. Thank you.
Good.
Let's
Okay.
see after
Enjoy your
the-
break. Yeah. Okay. See you. Bye.
Thank you.
So welcome back. Let's start the last session of the Astro-particle and Cosmology session at the ICHEP. So our last three talks in this session are all related to neutrinos. First, we are going to find out what a gigaton Baikal experiment can do. And then we are going to switch to the Chem3Net and Antares. So our first speaker is Grigory Safronov. Grigory, please, if you can start.
Can you hear me?
Very well.
Okay.
Also, I can see you, so that's good.
Okay, very well. So yeah, let me share my screen. Can you see the slides?
Yes. Very well.
Okay, so I am from INR Institute in Moscow, and I will talk about the status of Baikal-GVD experiment. Our experiment is a cubic kilometer scale underwater neutrino detector, which is under construction in Lake Baikal. Our gradually growing collaboration includes 10 organizations from 5 countries, and we have about 70 collaboration members. So the main purpose of the experiment is to study the astrophysical neutrino flux. So here on the left, this is the various sources of neutrino on Earth's surface and their flux. So basically our detector and analogous detectors in other places are sensitive to highest energy neutrino. So starting from hundreds of GeV to PeV range and further. So the lower side of this range is dominated by atmospheric neutrino, while starting from hundreds of TeV, we expect to see astrophysical neutrino. So astrophysical neutrino are very useful messengers in astrophysics studies. So they are propagated directly in interstellar and intergalactic medium. So they were first observed by the ICECube in 2013. So since then, a considerable sample of astrophysical neutrino events has been accumulated. However, the mechanisms of their generation are largely unconstrained. And of course, neutrino are essential ingredient of the rapidly growing multi-messenger observations field. So the principle of detection was the concept of large neutrino telescopes was first suggested by Moisei Markov at this conference in 1960. So this year we have a 60-year jubilee. So basically, our detector is a sparse array of optical modules submerged into the Lake Baikal. So, and we see the Cherenkov light from products of neutrino interactions. So basically, all neutrino interactions occurring via charged or neutral current are accompanied with a cascade, which is isotropic source of Cherenkov light. And however, for muon neutrino in charged current channel, the muon is produced, which has a large penetrating ability. So we can, so we have a pretty large effective area for muons, and also the angular precision is much better for muons. So here are some examples of muon and cascade events in Baikal. Okay. So there are several neutrino telescopes functioning now or under construction. So in Mediterranean, there is an Antares neutrino telescope working since 2008, which is followed by Chem3Net project, which is under construction now. On the South Pole, there is a famous ICECube detector, which is the largest detector, and it is growing. So the first phase of the Gen 2 upgrade is imminent, and the objective is to reach 10 cubic kilometers. And in Lake Baikal, we have our Baikal-GVD telescope. So our telescope is located in the south of Lake Baikal, 3.6 kilometers away from shore. The lake depth is approximately constant there, around 1,366 meters. And water transparency at our site is absorption length is about 22 meters, and scattering lengths vary on the season and from 30 to 50 meters. So the feature of our location is the stable ice cover over 6 to 8 weeks in February, April, which can hold heavy machinery. So this allows us to perform the detector deployment and maintenance during this time. So here's a brief history of Baikal project. So first experiments at this site started back to 1980, and in mid-90s the few strings detector was accomplished, and first atmospheric neutrino were registered in using NT96 detector with 4 strings and 96 optical modules, and an upgrade to the construction of Baikal-GVD detector started in 2015, and in 2016 the first full-scale cluster was deployed, and in 2020, or now, we operate 7 clusters, which include over 2,000 optical modules. So here are some photos from a winter expedition demonstrating the deployment process. Let me note that this winter there were very harsh ice conditions, which made the cable deployment process very difficult. But despite that, 2 new clusters were deployed, carrying 596 optical modules. So this is our the optical module, the sensitive element. Basically, it is the glass sphere which holds Hamamatsu 10-inch PMT with spherical photocathode, looking at oriented towards the lake bottom. Also, an optical module includes various sensors like accelerometer, compass, manometer, inclinometer, etc. Of course, the thermometer. And also each optical module has calibration LEDs for timing calibration. So the structural unit, actually the independent detection unit of our telescope is a cluster, which I have already mentioned. The cluster consists of 8 strings, and each string carries 36 optical modules spanning at depths from 750 to 1275 meters. So readout is organized in 3 sections, each holding 12 optical modules, and also each string holds various calibration devices like acoustic modems, LED calibration devices, and it is anchored at the lake bottom. So the control of the cluster is managed by the cluster center, which is located at 30 meters depth. And it holds trigger electronics, high voltage distribution, and data transmission electronics. So the trigger is organized as follows. So the cluster center reads an event and sends it to the shore center if in one of the sections, there were two adjacent models with charge deposited of around 4.5 and 1.5 photoelectrons in 100 nanosecond coincidence window. So this is an overview of the detector construction status. As I already mentioned, right now we operate 7 clusters with 216 optical modules. And we plan to deploy 8 more clusters by 2024, basically two clusters per year. So this will be more than 4,000 optical modules. Now I will talk about calibration systems of the telescope. Telescope is situated in the lake, and obviously there are water currents, and they cause up to 50-meter deviations of top optical modules with average speed of 0.5 centimeters per second. However, there are some extreme cases where when the drift occurs with speed of like 3 centimeters per second. So to calibrate the geometry of the detector, the system of acoustic beacons is deployed at each string. Basically, the time of acoustic signal propagation between beacons on neighboring strings is measured each 1 to 6 minutes, depending on the season. And each optical module position is reconstructed using piece linear interpolation. And the precision of the positioning is better than 20 centimeters. So here is the illustration of the drift of optical modules. So topmost picture is actually the bottom acoustic beacon. So one can see a pretty small drift, obviously, because it is anchored. But for topmost beacon, the drift is as large as 50 to 60 meters. So we have time calibration systems, each for interchannel calibration within one section. We use calibration LEDs inside each optical module. For intersection calibration, we have special LED matrix modules, which hold several calibration LEDs and generate flashes which propagate up to up to 100 meters away from the module. So here is the comparison of various calibration methods for LED calibration. One can see the 2 nanosecond spread, and also here is the drift of calibration based on LED matrix from run to run, and it does not exceed 2 nanoseconds. So our timing calibration precision is 2 nanoseconds approximately. We have also deployed a laser system for intercluster timing calibration for water properties monitoring. Basically, these are 3 technological strings carrying 5 dedicated lasers, which produce isotropic flashes of green light of length of 1 nanosecond. So this is the device itself, and here is the top view of the detector based on acoustic data. So here are the clusters, and one can see the technical strings instrumented with lasers between the clusters. And this is an example of laser event from 2016. So one can see that basically the whole cluster is illuminated by the laser, which is 60 meters away from it. And this is the intercluster synchronization cross-check. One can see the, well, between cluster 3 and 2. So one can see the 3 nanosecond offset, which can be corrected. Our detector operates at a rate around from 100 hertz to like few hundred hertz in more when environment becomes more noisy, which produces around 40 gigabytes per cluster per day to the shore center. This data is transferred via radio channel to Baikal-GVD, where and from it via Ethernet connection it is transferred to GNR, and at GNR all the data processing happens. So we have automatic data processing chain, the storage, and also the user analysis. Okay, so now I go to results. So I have already shown the picture of the detector rate here. One can see that there is a quieter period and then larger rate period. So this is due to biogenic noise in Baikal water. So basically the sediment layer reaches the detector and produces the biogenic noise somewhere in July and August and later. So we distinct our data taking period into quiet period. This is before the July, and later the period with more noise. So in quiet period we have 20 to 60 kilohertz per optical module, while for later period it's noise is much bigger. So of course this noise complicates the muon reconstruction procedure. So it consists of two steps: hit finding, which is the selection of signal hits and noise rejection, and track fitting. Basically now we fit the track with the quality function consisting of the chi-squared term based on time, and function of deposited charge and distance of optical module from the track. So here on the right, there are the results of the muon reconstruction. So basically, this is the atmospheric muon rate compared to atmospheric muon Monte Carlo simulation. So we have here the downgoing muon region and upgoing muon region. So here the disagreement with Monte Carlo is demonstrated. And in upgoing region, this is the reconstructed atmospheric muons. And actually, this region is our signal region. So these reconstructed muons constituent background to our neutrino reconstruction procedure. So to select the muon neutrino, we have developed a set of cuts based on Monte Carlo for signal and for the atmospheric muon background. So basically, we need to suppress this misreconstructed background by a factor of 10 to power 5 to 10 to 6. And the most powerful variable for us is fit quality function divided by number of degrees of freedom. So this is the plot here on the left. Basically, this is the distribution of this variable for atmospheric muon Monte Carlo and for atmospheric neutrino Monte Carlo. And black are the data points. One can see that there is a distinct shoulder which is formed by the atmospheric neutrino, And here we have a nice, here we can make a cut at around 32. So, and we can see the nice data and Monte Carlo agreement. Okay, in addition to this cut, we apply cuts on about 10 other variables. And here for our analysis, we use data set of for a quiet period of year 2019, which basically runs from April 1st until June 30th. So, which makes a total exposition of 323 days. And we have selected 57 neutrino candidates in this data set, while the expectation from atmospheric neutrino Monte Carlo is about 77 neutrino candidates, so 77 neutrinos. So here we have about 30% disagreement. However, the agreement in shape of distributions demonstrated here is pretty good. So here on the left, the number of hits per neutrino candidate distribution is shown. And here on the right, the angular distribution of neutrino candidates is shown. As already mentioned, agreement in shape is pretty decent. So for I also mentioned that for single upgoing muon, we have an angular resolution of around 1 degree for single cluster analysis. So these are event displays of few of the selected candidates. This is the largest event with 19 hits on 3 strings. And here are a bit smaller events. So here are the early hits are marked in red, while late hits are marked in blue. So these are all upgoing events. Okay. So on the next few slides, I will show results on the high energy cascade search with Baikal-GVD. So the effective volume for 100 TeV cascades, which is kind of border where we expect astrophysical signal. So the effective volume has reached around 0.35 cubic kilometers, which is close to ICECube effective volume for high energy starting events, which is 0.4 cubic kilometers. Here, the effective area for neutrino detection in cascade mode is shown. So we have around 1 meter effective area for 100 TeV, and it increases. So we, with this configuration, we expect around 4.2 events per year for the 7 cluster detector. So this was estimated using one of the IceCube feeds of astrophysical neutrino spectrum, which had a power minus 2.46. Well, there are, of course, other feeds available, but for these estimations, we use this feed. So now a bit more about this, about events which we have found. So we have analyzed year 2016, 2018, and 2019. So the full exposition is 364 days for a single cluster. So we have found 7 candidates with energy greater than 100 TeV and number of hits greater than 19. And also, but most of these events are downgoing. However, we have also found an upgoing cascade with energy 71 TeV, which is also very promising. This is an example of a cascade event in Baikal-GVD. So, and for cascades, we have for 100 TeV cascades, we have around 3 to 3.5 degree angular resolution and 30% energy resolution. So this is the preliminary map of events which we have found on the galactic, with respect to the galactic plane. So this is made based on the Fermi library. Okay. Okay. We also perform multi-messenger studies. We have produced a neutrino flux limit for the neutron star merger event, which occurred in summer 2016. We have other neutrino experiments, Antares and IceCube. We have performed search for events in cascade mode in plus minus 500 second window, and also in 14 days window after the merger. However, no events were found, so we have set a limit on the neutrino flux, which is a bit less strict than Antares, because in 2016 we were operating just 2 clusters and they were not really stable. So right now our possibilities are better. Okay, so now I go to my summary. So since April 2020, we operate 7 clusters over 2,000 optical modules. We have developed accurate methods for calibration and positioning. Also, we developed muon reconstruction techniques, and we a decent agreement of the results with the Monte Carlo expectation. And we also demonstrate a set of 57 good muon neutrino candidates, which was selected in 323 days in single cluster lifetime in 2019. We also have found a set of 8 high energy cascade alert events, which were in 1,364 days single cluster lifetime in over the 3 years. So, of course, we are still work in progress. A lot of things are changing and upgrading. One of our main targets now is to perform a multi-cluster analysis. Okay, that's all.
Thank you very much, Grigory. And this is impressive. So you see this Baikal detector like enlarging and enlarging. This is very nice. So I'm looking forward to see the astrophysical neutrinos from you. Are there any questions? Let me see. Yeah, or it seems that Ralph might have a question.
Ask questions interactively. Yeah. Okay. So thanks. It's very nice to see the GVD data, and it looks very promising. Now, if you look at page 16, you showed at the upper right side the agreement or the comparison with Monte Carlo, and now the atmospheric muons. It looks like you predict quite a higher number, and it's probably the same Monte Carlo you use for the neutrinos. And then later you also find a higher number for the neutrinos. So is that somehow related, or is that something that you should worry about, or do you understand that disagreement? Because I was hoping that like the atmospheric muon Monte Carlo is like a benchmark for you to see whether the muon reconstruction works well, whether it's upward going or downward going, but you still have some tension here.
Yes, so basically we have, we actually developing Monte Carlo right now. So right now it is pretty basic. So we have we are working with quiet period of the data, which is the beginning of the year. However, there are still some discrepancies in noise. However, our Monte Carlo describes data well, but there could be some disagreement to non-perfect noise modeling. However, our cuts here separate the neutrino very well. So we think that we really see neutrino, and the actual cause of this difference is likely the not perfect description of the detector. So so basically the detector works not very stable. So we have sometimes the some sections switching off, etc. And we, of course, we work right now on run-by-run Monte Carlo, which will describe detector perfectly, but this analysis was made with a bit not that perfect detector description. So we expect that when we produce more precise Monte Carlo with all the detector configurations described, we will get better agreement.
Okay, thanks a lot. Yeah, but then we have a good path to have absolute sensitivity now. Thanks a lot.
Okay, I don't see any other raised hands or microphones turning on. Yes, there's Marcus.
Yeah, maybe a follow-up question on that. So if you have now this half a cubic kilometer detector, maybe instead of looking for Monte Carlo agreement of atmospheric muons, you could also look for partial detectors like the upper, lower part, and see if muons identified in the upper part also show up in the lower part. So it would be like a database. Maybe you have already looked into this. Some database check for reconstruction efficiency is what you would expect from Monte Carlo. So this is just a comment.
Okay. Yeah, for upper base, yeah, we actually something which I already mentioned. Yeah, something which we try to overcome is the noise in upper layers of the detector. So that's a kind of difficulty for us. We work on run-by-run Monte Carlo, which will describe this noise very well. But yeah, to extend the data set and do all these cross checks, yeah, we need a good run-by-run Monte Carlo. So yeah, that's something we work on.
Okay, thank you. So let's thank Grigory again, and we are going to switch to galactic neutrinos, and the speaker is Viviana Niro. Viviana, please, you can share your screen.
Is it okay?
It's perfect.
Okay, sorry, I didn't hear.
I was with my microphone switched off, so
okay.
Please go ahead.
Yes, so I will talk about neutrinos from galactic sources. In particular, this talk is based on this latest work that I done here in Paris. I'm a Marie Curie individual fellow at IPC in Paris. So just a short introduction about cosmic rays. Cosmic rays have been first discovered in 1912, and the observed energy spectrum is described by a power law with an index of about 2.7 up to few PeV, where the spectrum gets deeper and a feature that is called the knee originates. What is important, the Ni, because the Ni is believed to mark the maximum energy for cosmic ray accelerator by galactic sources. Since I will focus on galactic sources in this talk, this is why it is important, this energy of few PV. The connection with neutrinos is that the neutrinos are particles that rarely interact with matter, so they do not feel the magnetic field. And moreover, they can permit to discriminate between leptonic and hadronic scenarios. For this reason are, let's say, smoking gun signature of cosmic ray accelerator. There have been several work for calculation of neutrinos coming from galactic sources at Chem3 detector. In particular, here I listed some of the work. For example, specific Milagro sources at ICHEP has been considered in these two papers, and neutrinos from RxJ, Vela Junior, and so on have been considered in these papers. And here I will focus mainly on neutrinos from this source, IOC J1825. Just a quick summary about Chem3 detector. So currently, as I said before, there is the IceCube detector that is taking data and is completed since the end of 2010. The South Pole, and the other planned Chem3 detector is the Baikal detector we have heard before, and since 2020 has 7 cluster with an effective volume of 0.35 kilometer cube. And in this talk I will focus mainly on the planned Chem3 net detector. This consists of different modules. One is called ARC, that is mainly for astrophysical sources, and one ORCA that is mainly for oscillation studies. And here you can see the two building blocks for Chem3 net ARC. So just a quick summary about what's the status about neutrinos. We have a diffuse flux measured by IceCube with about 60 events above 60 TeV, and an evidence for neutrino emission coming from the blazar TXS 0506. Here I will not focus about these neutrinos, but I will focus about searches for point sources neutrinos. And here you can see the sensitivity of IceCube for different spectrum, like e to the -2, e to the -3, and e to the -2 with an energy cutoff. And I show this picture because you can see that IceCube has an optimal sensitivity for sources in the northern hemisphere, while it's less sensitive to sources located in the southern sky using track events. However, using cascade events, for example, in this latest figure, you can see that the sensitivity can increase also for the sources in the southern sky. Here is a comparison between the sensitivity to point sources for e to the -2 spectrum, and it's a comparison between Chem3 net and IceCube. IceCube is this blue line, Chem3 net discovery potential is this red line, and I show this picture just to show that how Chem3 net can improve the sensitivity to sources in the southern sky. For the discovery of Pevatron sources, a multi-messenger search is mandatory because gamma ray data are necessary for a correct estimation of neutrino fluxes from point sources. And just as a reminder, the characteristic of a gamma ray Pevatron sources is an hadronic hard spectrum that descends at least up to several 10 of TeV, and for this reason you need a gamma ray experiment with sensitivity up to about 100 TeV to make a correct prediction. For this reason, the recent results by the Hawk collaboration have been extremely important. There has been a catalog, it is called Hawk catalog, released in 2017, where 39 sources were identified, and so very high energy sources that emits about at energy of TV. And after that, there was another studies in this, in particular in this paper in 2019, where 9 sources have been identified that emit above 56 TV. And here you can see the distribution of the sources, and most likely all of them are of galactic origin. Among the sources, you can see here in this plot the 3 most luminous sources, and among these we have this source in gray, that is EOC J1825, that is the most luminous in the multi-TV domain. And since it is the most luminous, is one of the first that should be searched for, in this case with a neutrino telescope in the northern hemisphere, because of the position of the source. So here I report just for completeness the spectrum that of the source given by in this EOC catalog. And you can see that this source has an hard spectrum. The spectral index is about 2.12, has a cutoff of 60 TeV more or less, and an extension of 0.53 degree. So the sensitivity of Hawk to the high energy spectrum of this source is important for making a correct prediction for the neutrino flux. And moreover, this source overlaps with 2 sources detected by Hess. One is a very bright source, and one is much weaker. Here we did a study of of the region where the source is found using Fermi-Lat data, and this is the result for different band in energy. And you can see that at low energy, the emission coincide mainly with a pulsar. At higher energy, the emission comes mainly from the position of the Hess sources, the brightest of the Hess sources. And while at even higher energy, we have that we can see with the Fermi data that the emission is not Gaussian. And here with this green circle is where the Hawk sources have been seen, and the dashed green circle is the circle that encodes the 1 TeV emission from Fermi-Lat. And this dashed green circle is about of radius of 1.5 degree. So here you can see a summary of what I said before. In blue points is the sources, is the spectrum detected by the Hawk collaboration, and this is, has been extracted under the assumption that the source is a Gaussian morphology with an extension of 0.53 degree. This in black is the spectrum extracted using Fermi-Lat data, and 1.5 degree is the opening angle that encodes the 1 TeV emission as observed by Fermi-Lat. And this discrepancy can be due to a complex source morphology, as you've seen in the previous slide. At high energy, the emission from is given by using Fermi-Lat data is not Gaussian. So using this information, we have estimated the neutrino fluxes in 2 cases. One case is considering the spectrum and extension given by the Hawk collaboration, and one case is in which we have normalized the flux using the Fermi-Lat data, and we have used a bigger opening angle of 1.5 degree. So here is the expression for calculating the neutrino event at, in this case, at ChemTreeNet. So there is a convolution with the effective area and some factor that takes into account the visibility of the source at ChemTreeNet and the reduction factor that takes into account the fact that not all the signal will be detected by the neutrino telescope. We have considered a resolution of 0.1 degdee, that is the one from ChemTreeNet and ARC detector. So here is the effective area as a function of energy. We have used the effective area here in a solid line, where we have taken into account the so-called trigger efficiency. That is a way to optimize the effective area for energy above 1 TeV. And here on the right, you can see the neutrino spectrum expected for this source, actually the neutrino rate, and in yellow, the atmospheric background. So you can see that the event that you expect from these sources are always above the background, but to estimate at which level you can detect this source, we have used a statistical significance method. So we have defined the p-value as used in the Atlas and CMS node, in which practically you do a comparison between what you expect from data that follow the signal plus background distribution with what you theoretically expect from the background only case. So doing that, here are the results. One is for the case of spectrum as given by the HOC collaboration and for a running of 10 years of ChemTreeNet, and you can see that you can reach a p-value of about 4 sigma as long as the energy threshold is, of neutrino is about 10 TeV. And here is the case of studying the more extended region, the one where the normalization is given by the Fermi-Lat result. And so we have studied a bigger opening angle. And in this case, we can see that roughly 5 sigma can be reached in 10 years with an energy threshold of about 10 TeV. So here are my conclusions. First, I want to say that the Baikal detector will have a discovery potential similar to the ChemTreeNet for this source. Concerning ICECube, most probably the cascade channel is the most promising way to discover this source. However, one should add that Chem3 detector in water will have a better angular resolution to cascade event respect to what expected from ICECube, that is about 10 degrees. And in general, combined analysis probably of different Chem3 detector could improve the sensitivity to this source. And finally, since this is the most luminous source detected by the HOC in the HOC catalog, will it be the first Pevatron sources detected in ChemTreeNet? Thanks.
Thank you, Viviana, for all these nice calculations. So are there any questions for Viviana? I see no hands raised. Ralph.
Yeah, thanks, Viviana. Question from my side. You use the optically thin source. This is your assumption, isn't it? That you can link the gamma rays directly to the neutrinos.
Yeah, yes, the gamma ray neutrino are just, I mean, the neutrino spectra is calculated from the decay of pion, kaons, and muons. You just have to follow the decay chain.
Yes, but you assume typically one interaction only, or I mean, so you have you assume the photons come out of the source without a problem, so that you have that your predictions right now are the lower limit of the neutrino flux. Is that correct? Or
well, I mean, once you have the photon spectrum that is given by what measured by the Hawke collaboration, once you have that, I mean, this is why I showed what is the spectrum. Once you have this function, you make the assumption that this photon comes from pi 0 or eta, and then you can calculate the neutrino spectrum just.
Yes, but my point is you calculated in the assumption that like charged pions and neutral pions are democratically produced and that the photons come out of the source directly. Because if it was an optically thick source, you could have actually have more neutrinos coming out than because the gammas might be absorbed and the neutrinos not. So in this sense, I assume what the calculation shows is a lower limit of the flux.
Sorry?
That your calculation shows the lower limit of the neutrino flux you expect from those sources. Of course, assuming that all the photons are hadronically produced, that is not guaranteed. That's of course another, let's say, uncertainty we have in that. Yeah.
Yes, I mean, okay. This is. I think this was the most straightforward way to relate the gamma spectrum with the neutrino.
Sure. I see your point. I only wanted to say that that there is an additional uncertainty, because if you go to your last slide where you show the rates, the detection rates, yeah, then one might be a bit disappointed that even for the brightest source, it's not so, or where you have the sigma, let's say, that even for the brightest galactic source, we don't expect so many neutrinos to be seen.
Yeah, I mean, this is for 1 year, but this is what we found.
Yeah, sure. Okay, thanks a lot.
Thanks.
Okay. Any other questions? Let me check also the mattermost, but it seems not. Okay, so let's thank you again, Viviana, and let's move to the last talk of our session by Tommaso.
Yes.
Yeah.
I'm sharing the screen. Okay. So I try to share also my video. I don't know if you see me. Yeah. Okay. So good morning. And so I will talk about the recent results from the Antares Neutrino Telescope. So I'm talking about on behalf of the Antares collaboration. Okay, so originally this talk was organized in 3 parts. The first part spent for giving the motivation behind the neutrino astrophysics with Cherenkov underwater telescopes, but this part has been already introduced by the previous talk. So I will simply say quick things here. I will focus on the Antares overview, and then I will report on the selection of our recent results. So I will skip this part introducing the zoo of the possible sources and the reason of why the neutrino is a very promising, interesting probe of the most violent phenomenon in the universe. And even here, given you know already how is the principle behind the detection technique and behind the neutrino underwater detector. Let me stress here only one thing, that in this slide you find some implication concerning the background for astrophysical contribution. So the background is considered given by the atmospheric neutrinos and muons. So as you can find here, the neutrino, you are expecting that there is a bulk of atmospheric muons that are downward going. So the neutrino telescope have an effective optimized detection for upward going particles, neutrinos. And of course, there is an not removable background given by the atmospheric neutrinos that can be separated upon some energy cut. And we are expecting, as we saw, that the astrophysics neutrinos comes up after the threshold of above 100 petal 100 eV. So, but by the way, the atmospheric contribution can be exploited to study the systematics of the detector and also to perform some other searches, for example, neutrino oscillation. So I will start here the Antares description, starting from the collaboration. And in the colored nations, you see which are the members of our collaboration. The black stars are regarding the Antares collaboration, and you find them almost overlapping to the Kentrinet collaboration, which are represented here by the white circles. So we have more than 34 European institutes and 8 extra European institutes contributing to Antares and also Kentrinet. Antares, I will talk it in a while, is located here close by one of the detector of Kentrinet, while the other is more to the south. But however, Kentrinet has been already introduced previously, so I won't insist on this. I will pass directly on Antares. So Antares, you can find in this yellow spot where it is placed, about 40 kilometers away from Toulon coast, and at a depth of 2,500 meters below the sea level. And it consists of a grid of 885 optical modules. You can find here one containing 10-inch PMTs. And so you have these optical modules are organized in vertical streams. And you have overall 12 lines, 12 strings that are working since 2007. So we have more than 12 years of data taking, and so we are planning on data to be analyzed. The instrumented volumes is not that big. It's not compared to the multi-cubic kilometer that are the target for the next generation neutrino telescope like ICHEP, Baikal-GVD, and Kentrinet. But remember that Antares was the first undersea neutrino telescope working, and it paved the path for the next generation telescope in the Mediterranean Sea. Now, before proceeding with the analysis, just a few hints on the performances, and one of the most important is the angular distance, the angular resolution. So I express as the angular distance between the true and the reconstructed neutrino direction. So here you have the two, the slide is divided in two parts. So on the left you have the 4 track-like candidates, and on the other side the cascade candidates. You find that for track-like candidates, the angular resolution is below 4 degrees, sorry, 0.4 degrees for tracks like events, and above 10 TeV. So this is a very nice angular resolution if you want to do astronomy. And this is due, apart from the effectiveness of the various reconstruction algorithms, but also because of the property of water in which the detector is set, with very long scattering length and absorbing length. So also for the cascade, the angular resolution is below 3 degrees for a wide energy range, as you can see on the right. I have a problem in the broadcasting.
Maybe if you stop your video, this could help.
Yeah, I think, but I need to get back the comments from my, computer. I apologize for I don't know what to do. It has
check
been
on
blocked.
on top of your
yeah, no, I am pressing whatever I can press, but so I don't know, maybe for you can, I don't know if I can broadcast from a different, so unfortunately I cannot stop the sharing. So
I can maybe
I can stop it for you.
Yes, if you can stop it for me, it would be nice. I apologize for this inconvenience.
If you like, I can share the
yeah, it would be nice. I also would like to have the presentation slides. Okay. So, unfortunately, my computer has completely frozen, and I don't know how to. So it's strange that you still see. Did you unblock the screen? Because for my side, it's blocked.
Yeah, so I'm actually sharing my screen right now.
Okay. Okay, so I can proceed looking at on a different computer that I prepared. Okay, now it has been blocked.
Yeah.
So, okay.
Does it work now?
Yeah.
Who's sharing now, actually?
Okay.
Now it's Marcus, so it's working.
Yeah. Please, if you go on slide, let's proceed with Marcus. Thanks, Marcus, for your ability. So if you go on slide number 9, yes. So now I started the analysis, but before starting with the real physics, I want again to stress something on the performances. So we used the moon and sun shadow effects, so the effect on the atmospheric muon fluxes due to the shielding of the primary cosmic rays done by the sun or the moon to estimate our pointing accuracy and measuring the angular resolution for downward atmospheric muons. So you see here this slide divided in two. On the left, the moon result, the moon shadow results, and on the right, the sun shadow. So first we saw these two celestial objects with nice significance, and which are sketched in the colored boxes. And we were able to measure the angular resolution for the atmospheric muons and the sun analysis, which was the ultimate and improved with respect to the moon, still preliminary, but submitted for publication, is presenting a 0.45 degrees as an angular resolution. And also concerning the pointing performances, let's say the moon shadow and the sun shadow reveals that the pointing is consistent with the expectation. Next slide, please. Slide number 10. So slide number 10, here I start for the analysis with the diffuse fluxes. Diffuse fluxes here are concerning the full, not the full, but the improved data set from 2007 to 2018. You can find here two plots, so divided in track-like events and cascade events on the right. And you can see comparing after the quality cuts and the final cuts, selecting the best areas, let's say at the right part of the energy range, where you can have the best disentangling between the background, the atmospheric background, and the possible cosmic source. You have that data for both tracks and cascades are a bit, the remaining data are a bit enhanced with respect to the simulation. So if you go to slide number 11, we were able to evaluate the excess that we have, which is not that big, but it's a mild excess, 1.8 sigma. And we fit here are reported our best fits for the power low spectrum parameters. So the gamma, the exponent 2.3 plus minus 0.4, and the normalization factor. So these results are compatible with the ICHEP diffuse flux, even though it remains a bit in the middle between the findings of ICHEP. So you would remember the tension between the two main data sets of passing muons and the high energy starting events. We have about 2 sigma tension. If you go in slide number 11, here there is a new analysis which is still not fully completed, but the preliminary results are very nice. The atmospheric neutrino cascade fluxes. On the left, you find the reconstructed energy distribution compared with expectation. And on the left, on the right, bottom right, you have the unfolded distribution, which separates the contribution of muon neutrinos and electron neutrinos. And say you can see that the Antares results in black points are matching nicely with the previous measurements provided by IceCube. In slide number 13, now I started talking about the results for point-like source searches. So we extended recently the search to full sky, and you have here the picture of the sky map. The blue point markers and the red circles are Antares findings for respectively tracks and showers. And together with this sky map, you have also the source some source position in the galactic plane, and the IceCube has a tracks, but we didn't find any strong correlation on this, so we were providing upper limits and improve our sensitivity. Next slides is showing this. You have again the map. In this time, it is a p-value, pre-trial p-values map, where you can find marked in red the most hotspots for this p-value map, and I will talk it later because it is found inconsistent with some interesting event, let's say, in the multi-messenger scenario. But here, just to stress that in the southern hemisphere, like has been even previously showed by Viviana presentation, Antares is challenging also with respect to IceCube. And here are present on the right the combined search of Antares and IceCube. You have the two plots. On the left, you have these plots are dividing the sources according to the spectrum. So on the left, you have a harder spectrum. On the left, on the right, you have the softer spectrum. And you can see in green the combined results between Antares and IceCube, and you see that the ratio is showing up that this combined sensitivity can push to a factor 2 the sensitivity. Nevertheless, I would like to stress that if you consider the right plot where the soft spectrum is the sources with the softer spectrum is considered, Antares is quite determinant because it is more sensitive at lower energy with respect to IceCube. If you go to slide number 15, here we also performed some staked analysis, and the most promising opportunity was represented by radio galaxies, which is highlighted in red in the table. But at the posterior p-value, let's say, show that we couldn't even in this case find some strong correlation. A particular attention was given by the Blaser MG3 J225517 that was also found in coincidence with a very interesting IceCube track. You can find on top, in the central plot on top, the field of view centered around the Blaser, and the circles are in green the IceCube, and in blue the Antares confidence, 68% confidence region pointing towards this field of view of the tracks detected by the two experiments. On the bottom right, instead, you have the light curve plots in which are overimposed as vertical dashed lines. In blue, the Antares track and the occurrence, and in green, the IceCube. So even combining IceCube and Antares, we can't get much than 2.6 sigma. So it is very interesting, but not determinant. If you go in slide number 16, were investigating also the possibility that the galactic plane could give some contribution that could explain the tension between IceCube passing events and starting events. but the joint analysis of Antares and IceCube started to constrain one of the most promising phenomenological model, the K-array gamma model, excluding a part of the model, let's say, and leaving a few chances, maybe even to the second option provided by the model with a 5 PV cutoff. In the end, what we could state is that the galactic neutrino looks not to provide more than 8.5% to the total diffuse flux detected by IceCube. If you go in next slide, so we also had a chance to evaluate gamma ray bursts. There's about 100 gamma ray bursts that were analyzed, but no coincidence found. And so upper limits were given, together with also some follow-up of 3 most promising gamma ray bursts from Hessen Magic collaboration. You can see also, again, no tracks were detected by Antares, both in time and space. So we only put limits. Next slide. We have also here we also had I want here to present Antares dark matter results in combination with IceCube. So I would concentrate on the right part of this plot for saving time. And the combined analysis considered the annihilation of dark matter, possible annihilation of dark matter in the galactic center. And you can see in the right plot the dashed blue and green lines, which are respectively for the separate upper limits from IceCube and Antares, and in red the combined analysis, which is, let's say, improving the sensitivity. Next slide. Okay, I will go to the end of this talk talking about an intense program of multi-messenger, which Antares is bringing ahead since many years. So here is sketched the network of other experiments and collaboration covering the photon spectrum, so gamma rays, experiment on satellite and ground-based, or radio optic X-ray, again with satellite ground-based experiments, other neutrino experiments like the both mentioned IceCube and GVD, and shower array ground-based experiment for the ultra-energy cosmic rays and gravitational waves for the Virgo League Observatory. Next slides. So Antares is getting the triggers from some of these experiments, providing their alerts, our alerts to a network of these experiments. For example, here is sketched the constraints for real-time alerts given by Antares. So you have to provide a quick response within 5 seconds. Since the detection of some interesting candidate, these candidates should respect constraint of angular resolution, energy ranges that could, let's say, interest different kind of detectors, and also maybe use some combination of some particular requirements, like having some doublets of neutrinos. So in the end, all these constraints shows up in giving an alert in about 40 alert periods to this network experiment that are detectors that are shown in this picture. Next slide, please. Of course, Antares also was trying to follow up some particular interesting and important alerts and occurrences of multi-messenger events. So here is the famous TXS 0506/056, which found, let's say, that the first evidence, strong evidence of strong correlation of IceCube track with high energy gamma ray emitter. And but Antares, fortunately, even repeating the searches in 3 different ways, couldn't find any neutrino coming from this direction. So unfortunately, we couldn't provide our detection. In next slide, I also want to mention that we are participating to the alerts from Virgo LIGO, and we got more than 20 alerts. We did more than 12 follow-ups, but unfortunately we didn't have any evidence on neutrino. Even for the one of the most interesting, the neutron-star merger events, with this sketch here. But in this case, the alignment is of the axis of this event was not along the line of sight. So maybe the fluence of neutrinos was biased with this. Next slide. Here I want to mention the other main achievements that I couldn't have the chance to discuss here because of time constraints, which are covering other analysis on point like sources or other correlation searches with IceCube, other kind of sources like radio burst, gamma ray burst, and neutrino oscillations and magnetic molecules. So this for the pure astrophysics and physics side, but also an underwater, undersea detector offers the possibility for multidisciplinary science. So here there are also results for sea and earth science searches. So last slide here is that I want to summarize. So neutrino Antares is the first undersea neutrino telescope in the Mediterranean Sea, and it is running since 12 years, and it continues taking data with quite nice stability and performances. We presented this, we had many results in many different, I here presented only a selection of these. And we are particularly proud of our multi-messenger program. And for the future, until we unplugged the power, we still to take data and to improve our analysis, included the full lifetime. So thank you very much, and sorry for the inconvenience.
Thank you, Tommaso. And actually, it wasn't such a big inconvenience. Yes, it was fine. Thank you also, Marcus, for sharing the screen. Any questions for Tommaso?
I ask a quick question.
Please go ahead.
So I also have control of the slides. It's very convenient for me right now.
Yeah, thanks.
So I was wondering, if you see my cursor, this kind of axis here looks very intriguing. Can you maybe comment on that?
The big one.
Yeah. So
well, despite the fact that this is very big and wide, it is, and note that this map, it is a pre-trial event. So with the post-trials, you have a breakdown of all these red spots, let's say. So we can say nothing but commenting that apparently we can say nothing.
But the extension that you see here is indicating some pre-trial access that corresponds to like a few degree source. Is that correct?
Yeah. Well, as far as I understand, there is not particular concentration of interesting source there. So the statistics.
Okay, thanks.
Okay, thank you. I don't see any hands or any other microphones turning on. I have a question, Tommaso, because this I really don't know. How do you search for the magnetic monopoles in Antares?
Okay, the question is how we do.
How do you search for the magnetic monopoles?
So the magnetic monopoles are searched. There is a publication we did mention in one of the latest slides. So if you look at the one with the dolphins, you should have the reference. And yes, that's one. The Journal Energy Physics 07/2015. So the search is based on a dedicated trigger events, which are looking for slow events.
Okay, so you're looking for the slow events. Okay, thank you. I don't see any other questions. So I think we should thank all the speakers of today and of the previous days as well. And We have scheduled now a 10 minutes break, and then we should resume with discussions. But what I would like to propose, if you agree, is to just stay here, and if there are any discussions, to just continue, and people can also take some coffee meanwhile. Does it sound good?
Yes.
I don't know if there are any discussion. Actually, I've seen just one question from Kostas on the chat for the talk on the AMS. I don't know if you want to elaborate, Kostas, on that. And
yeah, hi. Yeah, I just wanted to ask about to elaborate about the antiproton spectra, how the fits change by either including another dark matter species or so I understood. So if the mass for the dark matter particle is there such that the fits are, you improve the fits particularly at the lower end rather at the high end, but then it seems there is still some room to maneuver.
Okay. And then in any case, I see that the speakers, they're not here, so it's
yeah, okay.
Okay. So that's, none of the US people is here. I think yeah. So I don't know if somebody else has some other subjects that would like to discuss, or some specific questions to the speakers. Okay. So it does not really seem so. Then I think we should just stop the session if there's nobody that would like to ask anything special or to discuss something. Yeah. So I think also I speak also for the other conveners of the Astro-particle and Cosmology that would like to thank you everybody that joined our parallel session, and also the speakers for presenting and for all the questions that were posed here. And I don't know if Marcus or Kostas would like to also say something.
Yeah,
goodbye.
I agree with you that we thank, of course, all the speakers and also the participants for sticking with us and contributing to the session. Thank you.
Thank you, Luke.
Yeah, I would also like to thank everyone, all the speakers and all the participants and the other session conveners for all the effort and try to make this happen despite all the circumstances. So thank you all.
Okay, so I think that ends our parallel session on Astro-particle physics and cosmology, and I hope we meet at the next ICHEP, and let's hope that it's going to be in person. So, goodbye.
Bye-bye.
Thanks a lot. Bye.
Bye, thanks.
Bye.